Look up at the night sky on a clear evening far from the glow of city lights. That shimmering, ethereal river of stars arching overhead is our home, the Milky Way galaxy. It's a sight that has captivated humanity for millennia, a constant and familiar presence in the cosmos. But for all its familiarity, this grand spiral of hundreds of billions of stars holds secrets so profound, so utterly baffling, that they challenge the very limits of our understanding. What truly lies hidden within the dark heart of our galactic home, and just how much of its story remains a complete and total mystery to us? Today, we are setting out on a journey to explore the very edges of our cosmic knowledge, to shine a light on 25 of the most enigmatic and extraordinary phenomena ever discovered within the Milky Way. We are not talking about simple curiosities, but genuine cosmic head-scratchers that have left the world's most brilliant astronomers and physicists utterly perplexed. From invisible monsters lurking in the void to whispers of forces we cannot see, these are the puzzles that keep scientists awake at night, the cosmic riddles written in starlight and shadow that define the frontier of our exploration. This is more than just a list. It is a voyage into the great unknown that exists right on our galactic doorstep. Each mystery we will uncover is a testament to just how strange, dynamic, and wonderfully mysterious our universe can be. We will confront questions that probe the fundamental laws of physics, encounter objects that shouldn't exist, and piece together clues from a cosmos that is often far stranger than any fiction. So prepare to have your perspective shifted, because we are about to dive deep into the most compelling and mysterious phenomena of the Milky Way. Our journey into the galactic unknown begins with a force so immense it is dragging our entire galaxy and every galaxy nearby on a terrifying journey through the cosmos. We are right now hurtling through space at a staggering speed of over 2 million kilometers per hour, pulled by something we cannot directly see. This is the mystery of the Great Attractor. Located roughly 250 million light-years away in the general direction of the constellations Centaurus and Hydra, this colossal gravitational anomaly represents one of the most profound puzzles in modern cosmology. Think of it like a cosmic river, with the flow of countless galaxies all being drawn toward a single, unseen point in the void. Our Milky Way, our local group of galaxies, and even the immense Virgo supercluster are all just leaves caught in this immense current. The sheer scale of the gravitational force required to accomplish this is almost incomprehensible, suggesting the presence of a concentration of mass that could be tens of thousands of times greater than the mass of our entire galaxy. But what could possibly be that massive, and why can't we get a clear look at it? The answer to that second question lies in a simple but frustrating cosmic obstacle. Our own galaxy is in the way. To observe the Great Attractor, astronomers must peer through the crowded, dusty central plane of the Milky Way, a region we call the zone of avoidance. This part of the sky is so thick with gas, dust, and stars that it effectively acts like a dense fog, blotting out the visible light from the universe beyond. It's as if the most interesting room in the cosmic house is located directly behind a brightly lit, messy closet, and we're stuck trying to see through the clutter. For decades, this zone rendered a huge portion of our extragalactic backyard completely invisible to traditional telescopes. However, scientists are a resourceful bunch. They realized that while visible light cannot penetrate this galactic fog, other forms of radiation can. By using space-based observatories like NASA's Wilkinson Microwave Anisotropy Probe, or WMAP, and the European Space Agency's Planck mission, which map the cosmos in microwave wavelengths, along with radio and X-ray telescopes, we have been able to see the gravitational influence of the Great Attractor indirectly. These missions have painted a picture of the large-scale flow of galaxies, charting the irresistible pull of this hidden monster. The data confirms that the Great Attractor is not the end of the line either. It now appears that an even larger structure, the Shapley supercluster, which lies beyond the Great Attractor, is exerting its own gravitational pull, making the entire cosmic tug of war even more complex. So, the central question remains wide open. What is the true nature of the colossal mass that dominates this region of space? Is it an unfathomably dense knot of dark matter, a supercluster of galaxies we have yet to fully catalog, or something even more exotic? The Great Attractor stands as a humbling reminder that some of the universe's biggest secrets are hiding, quite literally, in our own backyard. But while we are being pulled toward an unseen giant, our own galaxy is no passive bystander in the cosmic arena. It is a predator, and this brings us to our second profound mystery, a process that reveals the violent, dynamic nature of galactic life, galactic cannibalism. Far from being an isolated island, the Milky Way is the dominant force in its own local neighborhood, and it grows by consuming its smaller companions. The most striking example of this happening right now is the ongoing destruction of the Sagittarius dwarf elliptical galaxy. Imagine a galaxy a mere 10,000th the mass of our own, on a long, looping orbit that repeatedly sends it slicing directly through the plane of the Milky Way's disk. With each pass, our galaxy's immense gravity acts like a set of cosmic claws, tearing the smaller galaxy apart. The primary mechanism of this destruction is the sheer power of tidal forces. Think of it this way: the side of the dwarf galaxy that is closer to the Milky Way center feels a much stronger gravitational pull than the side farther away. This difference in pull, the tidal force, stretches the smaller galaxy, pulling it apart like warm taffy. It systematically strips away its stars, its gas, and even its elusive dark matter. But these stolen stars are not simply absorbed and lost. They are flung into vast ribbons of light that orbit the Milky Way. These are known as tidal streams, and they wrap around our galaxy in a giant, complex halo, a ghostly remnant of a meal in progress. The stream of stars from the Sagittarius dwarf is so immense that it completely encircles the Milky Way, a cosmic serpent eating its own tail, a permanent scar from a collision that has been ongoing for billions of years. What does this violent history tell us? It fundamentally reshapes our understanding of how galaxies form and evolve over cosmic time. The long-held picture of galaxies forming in isolation and then living quiet, solitary lives is simply wrong. Instead, we now see a universe built on hierarchy and merger. Large galaxies like our own were assembled over billions of years by digesting dozens, perhaps even hundreds, of smaller dwarf galaxies. The Sagittarius dwarf is not an anomaly. It is a standard chapter in the biography of a spiral galaxy. By studying the chemical composition of the stars in these tidal streams, astronomers can perform a kind of galactic archaeology. They've discovered that stars from the Sagittarius stream are generally older and contain fewer heavy elements compared to the stars in our own galactic disk. This tells a story. The dwarf galaxy it came from was an ancient building block of the universe, one that formed its stars early on, before many generations of supernova had enriched it with metals. Its consumption is literally adding ancient stellar fossils to our galaxy's population. This process of galactic cannibalism is also a glimpse into the far future. In about 4 billion years, the Milky Way is set to undergo its own ultimate merger with the Andromeda Galaxy. The serene spiral we see today is both a product of ancient violence and a participant in the continuous, dynamic dance of construction and destruction that defines our evolving cosmos. Yet for all the immense gravitational power the Milky Way wields, there remains a profound and unsettling truth about our home. Most of it is completely invisible to us. The grand spiral of stars we see, the brilliant arms traced out by nebulae and clusters, that entire luminous structure accounts for a mere fraction of the galaxy's true substance. The overwhelming majority of the mass holding our galaxy together is made of something we cannot see, touch, or directly detect. This is the enigma of dark matter, and it forms our third great mystery, an invisible, all-pervading presence that is the true architectural backbone of the Milky Way. Imagine if you could see the galaxy not in light, but in terms of its mass. The beautiful spiral disk would look like a small, bright coin suspended at the center of an enormous, diffuse sphere of darkness. This is the dark matter halo, a vast, spherical cloud that envelops the entire visible galaxy and extends far, far beyond its stellar boundaries. It contains roughly 85% of the Milky Way's total mass. That means for every single atom, every star, every speck of dust you can see, there is about 6 times more mass in a form that is utterly mysterious. This isn't just some minor component. This is the primary ingredient, the hidden framework upon which the luminous galaxy is built. Without the immense gravitational grip of this dark halo, the Milky Way would simply fly apart. The stars in our outer regions orbit at speeds that should, according to the laws of gravity and the amount of visible matter, send them hurtling off into intergalactic space. The fact that they don't is our first and most crucial clue to dark matter's existence. This evidence comes from studying galactic rotation curves. A rotation curve is simply a graph that plots the orbital speed of stars and gas against their distance from the galactic center. According to basic orbital mechanics, you would expect stars farther from the center, like the outer planets in our solar system, to move much more slowly than those closer in. But when astronomers measured these speeds in the Milky Way and other spiral galaxies, they found something startling. Instead of falling off, the rotation curves remain flat. Stars on the outskirts of the galaxy are orbiting at virtually the same high speed as those near the inner regions. The only plausible explanation is that there must be a huge amount of unseen mass distributed throughout the halo, providing the extra gravitational pull to keep these stars whipping around at such incredible velocities. So, if we can't see it, what exactly is dark matter? We know what it is not. It is not normal matter, the protons, neutrons, and electrons that make up everything from stars to planets to our own bodies. It doesn't emit, absorb, or reflect light, and it appears to interact with normal matter almost exclusively through gravity. It doesn't seem to form into dense objects like stars or planets, and it passes through both itself and normal matter with ghostly ease. This last point is critical. If dark matter particles interacted strongly with each other or with us, we would have detected them by now. Their very elusiveness is a defining characteristic. This has led physicists to propose some truly exotic candidates. The leading theoretical contender for decades has been a class of particles known as WIMP, or weakly interacting massive particles. As the name implies, these would be particles that have a significant mass, perhaps many times that of a proton, but which interact with normal matter only through the weak nuclear force and gravity. This would make them incredibly difficult to spot, as they would barely notice the world of atoms and light. To find them, scientists have built incredibly sensitive detectors deep underground, in old mines and tunnels, shielded from cosmic rays. These experiments wait for the minuscule shudder that would occur if a WIMP ever, very rarely, bumped into the nucleus of an atom in their detector. So far, after years of searching, these detectors have remained silent. Another fascinating candidate is the action, a hypothetical particle that is incredibly light, trillions of times lighter than an electron, but which could exist in such vast numbers that they would collectively account for the missing mass. Actions were originally proposed to solve a completely different, esoteric problem in particle physics, but they happen to have the right properties to be a compelling dark matter candidate. Unlike WIMP, actions would not be detected through nuclear recoils. Instead, scientists are building novel experiments that use powerful magnetic fields to try and convert these ghostly particles into faint but detectable photons of microwave light. It's a long-shot, high-precision endeavor that represents the creative lengths to which physicists must go to hunt for this invisible substance. The true nature of dark matter remains one of the most significant open questions in all of modern science. It is not a minor puzzle. It is a fundamental gap in our understanding of the universe's composition. Every time we look at the graceful rotation of a galaxy or the way light bends around massive galaxy clusters, we are witnessing the gravitational signature of this unknown component of reality. It is the unseen architect of the cosmic large-scale structure, the hidden hand that guided the formation of galaxies like our own. Solving this mystery would not just tell us what the majority of our galaxy is made of. It would likely open a door to a whole new realm of physics, revealing a hidden sector of the universe that has been there all along, governing the fate of the cosmos from the shadows. Leaving the invisible grip of dark matter behind, we now turn our attention to a different kind of cosmic phantom, one that we can see, but whose origin story remains a subject of intense debate. Jutting out from the very heart of the Milky Way are two colossal, ghostly orbs of high-energy radiation, structures so immense they dwarf every other feature in our galaxy. These are the Fermi Bubbles, and they represent a relatively recent and stunning discovery that has completely reshaped our understanding of the galactic center's violent history. For centuries, astronomers mapped the sky in visible light, yet these gargantuan formations went entirely unnoticed. It wasn't until the launch of the Fermi Gamma Ray Space Telescope in 2008 that we gained the right set of eyes to see them. By scanning the heavens for the most energetic form of light, gamma rays, Fermi revealed a breathtaking sight: two vast lobes, one extending north and the other south from the galactic plane, each reaching a staggering 25,000 light-years into space. To put that scale into perspective, the entire visible disk of the Milky Way is only about 100,000 light-years across. This means these bubbles span nearly half the diameter of our galaxy, creating a figure that, if we could see it with our naked eyes, would dominate the night sky. The discovery was a monumental surprise. Here was evidence of a cataclysmic event, a massive release of energy from the galactic center that had blown these enormous cavities clear through the galaxy's gaseous halo. But what kind of event could possibly have that much power? The evidence points toward two primary suspects, each capable of unleashing such a titanic outburst. The first, and perhaps the most dramatic, culprit is our own supermassive black hole, Sagittarius A star. While it's relatively quiet today, the Fermi bubbles suggest that it wasn't always so serene. Astronomers theorize that several million years ago, Sagittarius A star may have experienced a period of intense activity, gorging itself on a vast amount of incoming gas and dust. During such a feeding frenzy, not all the material falls past the event horizon. Instead, powerful magnetic fields can funnel some of the inflating gas into two opposing jets, shooting out from the black hole's poles at nearly the speed of light. If Sagittarius A star's jets were pointed roughly perpendicular to the galactic disk, they could have inflated these giant bubbles over thousands or millions of years, filling them with high-energy particles that now glow in gamma rays. It's the cosmic equivalent of a sleeping dragon that once belched a pair of flames so vast they reached halfway across the galaxy. The second leading theory points not to a single monstrous entity, but to the collective fury of countless stellar births and deaths. The galactic center is an exceptionally crowded and chaotic place, home to numerous massive star clusters. If a wave of intense star formation occurred there in the relatively recent past, it would have created a huge population of massive, short-lived stars. These stars would have lived fast and died young, exploding as supernovae in rapid succession. The combined force of hundreds or even thousands of these simultaneous stellar explosions could have created a powerful galactic wind, a superheated shockwave that blew outward from the core, effectively puffing up the Fermi bubbles from the inside out. This scenario paints a picture of a starburst event in our own backyard, a period of frantic cosmic construction and destruction whose final echo is etched into the gamma-ray sky. So, which story is the true one? The clues lie in the intricate details of the bubble's structure and the specific energies of the particles within them. For instance, the edges of the bubbles are remarkably sharp and well-defined, which some scientists argue is more consistent with a sudden, jet-like eruption from the black hole than a more gradual wind from stellar explosions. Furthermore, the bubbles are also surrounded by a fainter, larger structure seen in X-rays called the E-Reseda bubbles, discovered by a German-Russian space telescope. This suggests the event had multiple phases or involved different forms of energy. The Fermi bubbles, therefore, are not just a spectacular sight, they are a fossil record. They preserve the evidence of a violent chapter in the Milky Way's history, a testament to the fact that the calm center we observe today is merely a temporary lull in a life cycle punctuated by episodes of unimaginable ferocity. They stand as a permanent reminder that even our own galactic home has a past filled with spectacular, high-energy drama. And as we move inward from these vast, high-energy bubbles, we arrive at the ultimate enigma, the very engine room of our galaxy, the galactic center. This is a place of extremes, a maelstrom of cosmic activity so intense that it defies easy description. Imagine a region just a few light years across, a mere pinprick on the galactic scale, yet containing a staggering concentration of mass and energy. At the very heart of this chaos sits the supermassive black hole known as Sagittarius A star, a gravitational monster with a mass equivalent to more than 4 million suns. It is the anchor around which our entire galaxy slowly turns, and the bizarre phenomena that play out in its immediate vicinity are some of the most compelling evidence we have for its presence and nature. To understand the strange behavior here, we need to look at the stars that are trapped in its gravitational grip. These are not ordinary stars in leisurely orbits. They are cosmic daredevils, whipping around the black hole at speeds that are almost unimaginable. The most famous of these is a star known as S2. Its orbit is an incredibly elongated ellipse that brings it breathtakingly close to the event horizon. At its closest approach, S2 is moving at a velocity in excess of 25 million kilometers per hour, a staggering figure that is nearly 3% of the speed of light. Following its orbit over decades has been one of the most powerful confirmations of Einstein's theory of general relativity. We can actually observe the effects of extreme gravity on the starlight itself, a phenomenon known as gravitational redshift, where the light from the star is stretched to longer, redder wavelengths as it struggles to climb out of the black hole's intense gravitational well. The very path of its orbit slowly rotates over time, a precise dance predicted by relativity known as Schwarzschild precession. These stars are not just objects, they are precision test particles, allowing us to probe the fabric of spacetime in a way that no laboratory on Earth ever could. But the strangeness doesn't stop with these whirling stellar sentinels. Sagittarius, a star itself, while generally a quiet and faint object in terms of radiation, occasionally erupts in mysterious and brilliant flares. These are not your average solar flares. Scaled up, we are talking about outbursts that can temporarily make the black hole's immediate environment 100 or even 1,000 times brighter in infrared and X-ray light. The cause of these dramatic flares is still a topic of active investigation. One leading idea is that they are caused by sudden, violent releases of magnetic energy. Just like the sun, the accretion disk of hot gas swirling around the black hole is permeated with powerful magnetic fields. These fields can become twisted and tangled, building up stress until they explosively snap and reconnect, a process that accelerates particles to near light speeds and unleashes a torrent of radiation. Another fascinating possibility involves unlucky asteroids or clumps of gas that wander too close to the event horizon. The immense tidal forces from the black hole would shred such an object into a stream of superheated debris, which would then glow intensely as it spirals into the abyss. These flares offer us a fleeting, violent glimpse into the complex and dynamic processes happening just outside the point of no return. Adding another layer of mystery to this already bewildering region are bizarre, thread-like structures that have puzzled astronomers since their discovery. These are the galactic center filaments. They appear as long, magnetized strands of energetic electrons, stretching for tens of light years, yet they are remarkably thin, like immense cosmic hairs strewn across the galactic core. They don't seem to be connected to any obvious source, and they point radially away from the vicinity of Sagittarius, a star. What could possibly create such organized, linear structures in the midst of such chaos? One compelling theory suggests they are the result of a past, much more powerful outburst from the black hole. If a jet of high-energy particles interacted with pockets of denser gas in the region, it could have sculpted these magnetic filaments, leaving them as permanent scars. Another idea posits that they are caused by the interaction of a cosmic wind with magnetic fields, creating structures similar to the patterns you see when iron filings align around a magnet, but on a truly galactic scale. Their very presence tells us that the energy flow from the galactic center is far more complex and structured than we ever imagined. All of these clues, the whirling stars, the sudden flares, the enigmatic filaments, paint a picture of a dynamic and violent environment. Yet they also highlight a fundamental limitation. Our view, the very center of our galaxy, is shrouded in thick clouds of gas and dust, obscuring our direct line of sight in visible light. It's like trying to observe the details of a bustling city square through a dense, perpetual fog. This veil forces us to rely on other forms of light, like infrared and radio waves, which can pierce the obscuring material. But this also means that there could be entire populations of stars or other exotic objects hidden from our view, lurking in the shadows just light years away from the central black hole. Could there be a dense cluster of neutron stars or smaller black holes, the remains of countless stellar collisions and deaths, swarming around Sagittarius, a star? The gravitational tides are so extreme that normal star formation as we know it should be nearly impossible, yet we see evidence of young, massive stars there, which poses its own separate puzzle. The galactic center is a realm where the known laws of physics are pushed to their absolute limits, a natural laboratory for the most extreme conditions in the cosmos, and it holds the key to understanding not just the life cycle of our own galaxy, but the fundamental behavior of matter and energy under the most intense gravitational strain imaginable. But what if the galaxy's strange signals weren't just confined to its chaotic heart? What if brief, impossibly brilliant messages were flashing across the entire cosmic canvas, so fast you could blink and miss them? This brings us to one of the most electrifying mysteries in modern astronomy: fast radio bursts. For years, these phenomena were ghosts from the deep universe, fleeting blasts of radio waves that for a mere millisecond would outshine entire galaxies, only to vanish without a trace. Their origins were a complete enigma, with theories ranging from colliding neutron stars to the energetic signatures of advanced alien civilizations. There were cosmic sirens calling from billions of light years away, their immense distances making them incredibly difficult to pin down. The critical breakthrough, however, didn't come from the far reaches of the cosmos. It came from an object right here in our own galactic backyard, a discovery that finally gave us a tangible culprit for at least some of these spectacular explosions. The key to unlocking part of this mystery was a star known as a magnetar. Imagine the core of a massive star that has collapsed under its own gravity, not into a black hole, but into a city-sized ball of ultradense neutrons. Now, compress that thought further. A magnetar is a neutron star pushed to an even more extreme limit, possessing a magnetic field so powerful it defies comprehension. We're talking about a field 1,000 trillion times stronger than Earth's. If a magnetar were located halfway between the Earth and the Moon, its magnetic pull would be strong enough to strip the data from every credit card on the planet. These objects are seething with pent-up energy, and they occasionally release it in violent starquakes and enormous bursts of X-rays and gamma rays. Then, in April 2020, one specific magnetar in our galaxy, named SGR 1935 plus 2154, did something unprecedented. As it was in a period of heightened activity, throwing off X-ray flares, several radio telescopes on Earth detected an incredibly intense, millisecond-long blast of radio waves coming from the exact same location. This was not just any radio signal. It was a proper fast radio burst, but one originating from within the Milky Way. For the first time ever, we had a front row seat to a local version of a phenomenon we had only ever seen from across the universe. The energy released was staggering. In that single millisecond, the magnetar emitted more energy than the sun puts out in 30 seconds. While this was still 1,000 times less energetic than the most powerful extragalactic FRBs, the connection was undeniable. We had caught a magnetar in the act. This single observation was a watershed moment for astronomy. It provided the first direct evidence linking at least some fast radio bursts to magnetars, instantly elevating one theory from speculative possibility to confirmed reality. But how does a magnetar create such a brilliant, fleeting flash? The leading theory involves a starquake. The magnetar's incredibly rigid crust, under immense stress from the twisting internal magnetic fields, can suddenly fracture, much like the Earth's crust during an earthquake. This seismic event on a stellar scale releases a colossal amount of energy, shaking the magnetar's magnetic field. This, in turn, accelerates particles to near light speeds, and as these particles interact with the intense magnetic environment, they emit a massive, coherent shockwave of radio waves, the fast radio burst we detect. It's the cosmic equivalent of a giant, magnetic bell being struck, ringing out across the galaxy for a single, spectacular moment. The local detection from SGR 1935 plus 2154 did more than just identify a source. It gave us a crucial measuring stick. Because we knew its distance and could observe it across multiple wavelengths, we could precisely calibrate the energy of the event. This confirmed that the physics required to create such a burst is indeed plausible within the framework of a magnetar's extreme environment. It demonstrated that you don't necessarily need a truly cataclysmic event like a neutron star merger to power these flashes. A single, hyper-magnetic star having a bad day can do the trick. This revelation has narrowed the field of possible explanations dramatically, suggesting that magnetars could be responsible for a significant fraction, though likely not all, of the fast radio bursts we observe. It turns the mystery from an abstract, what could they be, into a more tangible, how do these magnetars actually do it? A question we can now investigate with a known, nearby example to study. The enigma of FRBs is far from completely solved, but thanks to a violent neighbor within our own galaxy, we are finally starting to read the signatures written in these millisecond-long cosmic sparks. Yet for all the strange signals we can trace back to known cosmic powerhouses like magnetars, there remains one signal from the past that stands apart, a singular event that continues to defy any definitive explanation. This is the story of the WOW signal, a 72-second burst of radio waves that, for one brief moment in 1977, looked exactly like the kind of message we might expect from an intelligent civilization beyond our world. It was detected by Ohio State University's Big Ear Radio Telescope, which was part of the long-running Search for Extraterrestrial Intelligence, or SETI, program. The telescope worked by scanning the sky as the Earth rotated, and any signal from a fixed point in space would initially grow in intensity as it drifted into the telescope's beam, peak, and then fade away as it drifted out, all over a span of about 72 seconds. And that is precisely the signature the computer printer recorded on August 15th of that year. The data itself was a string of alphanumeric characters representing the signal's intensity. The sequence read 6EQUJ5. An astronomer named Jerry Amon was reviewing the computer printout a few days later, and when his eyes fell upon that sequence, he was so stunned by its perfect profile that he circled it in red pen and wrote, "Wow." In the margin, giving the signal its now legendary name, the letters E, Q, U, and J corresponded to intensity values of 14, 15, 16, and 17, which were extraordinarily high. The signal was not only powerful, but it was also narrowband, meaning it was concentrated on one specific radio frequency, around 1420 MHz. This is a frequency that is naturally quiet, a protected band where radio noise from hydrogen and hydroxyl molecules is minimal, a band sometimes poetically called the water hole and considered a logical channel for interstellar communication. Everything about it, its strength, its duration, its narrowband nature, fit the predicted hallmark of a deliberate, engineered signal from the stars. The location of the signal only added to the intrigue. It originated from a point in the sky within the constellation Sagittarius, a direction that points toward the crowded center of our own Milky Way galaxy. This region is rich with stars, raising the tantalizing possibility that the signal had traversed the galactic core before reaching us. The immediate and obvious question was, and remains, could this have been it? Could this have been our first hello? The hunt for a repeat signal became an absolute priority. If it was a genuine transmission from another civilization, it should be possible to detect it again. The Big Ear Telescope, and later other powerful radio observatories around the world, pointed again and again at that same patch of sky. They scanned for decades, using increasingly sensitive equipment, listening for another whisper, another shout. Yet, the silence has been deafening. The WOW signal never repeated. Not a single trace of it has ever been found again, turning a moment of potential discovery into a persistent, haunting cosmic cold case. This profound lack of repetition is the single biggest argument against an intelligent origin. If it was a message, why was it sent only once? This has driven scientists to search tirelessly for a natural explanation. One of the most discussed theories in recent years involved the possibility of a comet. In 2016, an astronomer proposed that two previously unknown comets, which happened to be passing through that region of space in 1977, could have been the source. The idea was that the large clouds of hydrogen gas surrounding these comets might have emitted a narrowband radio signal as they were excited by the solar wind. However, this hypothesis was met with strong skepticism. Other radio astronomers quickly pointed out that the specific frequency of the WOW signal, 1420 MHz, is a protected band where such cometary emissions are not expected to occur with any significant strength. Furthermore, the comets were not actually in the precise beam of the telescope at the exact moment of the detection. The comet explanation while creative, has largely been dismissed by the scientific community for failing to align with the observed facts. Other natural explanations have been put forward over the years. Could it have been a signal reflected off a piece of human-made space debris? The timing and the specific orbit required for such a reflection make this extremely unlikely. Could it have been an instrumental glitch or an unknown form of terrestrial interference? The Big Ear telescope had two separate feed horns that looked at slightly different patches of sky a few minutes apart. A genuine cosmic signal should have appeared in both horns, but the wow signal was only detected in one. This is puzzling, but it doesn't definitively rule it out. The signal could have ceased in the few minutes between the two scans. The very fact that it was never detected again, however, makes it difficult to test any of these hypotheses thoroughly. It exists as a single, perfect data point in history, an anomaly that refuses to be neatly categorized. Decades later, the wow signal endures not because we have the answer, but precisely because we don't. It remains the most compelling, best documented candidate for a potential extraterrestrial transmission in the entire history of SETI. It was a signal that perfectly matched the profile of what we were looking for, appearing in the most logical place, at the most logical frequency. Its power and its uniqueness continue to captivate the imagination. It serves as a powerful reminder of the challenge of searching for needles in the cosmic haystack, especially when the needle only seems to appear once. It underscores the fundamental difficulty of doing science with a non-repeatable event. The wow signal is a ghost, a one-night stand with the cosmos that continues to whisper a tantalizing question. Were we, for just 72 seconds in the summer of 1977, not alone in the universe? Without a repeat performance, it remains frozen in time, our most enigmatic and cherished celestial hello. Now, let's shift our perspective outward, from the strange signals within our galaxy to the vast cosmic void that our entire Milky Way calls home. It's a staggering concept, but we are not just inhabitants of a galaxy. We are residents of a colossal cosmic desert, a bubble of relative emptiness in the grand structure of the universe. This is the KBC void, named for the astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, who presented the most compelling evidence for its existence. Their work suggests that our galactic neighborhood sits inside an immense underdense region, a spherical void roughly 2 billion light-years across. To grasp that scale, imagine a sphere so vast that light, traveling at its incredible speed, would take 2 billion years just to cross from one side to the other. Within this unimaginable volume, the density of galaxies, galaxy clusters, and matter in general is significantly lower than the cosmic average. We are living in what amounts to one of the largest known holes in the cosmic Swiss cheese. This discovery presents a direct and profound challenge to one of the most fundamental tenets of modern cosmology, the cosmological principle. This principle essentially states that on sufficiently large scales, the universe is both homogeneous and isotropic. In simpler terms, it means the universe should look roughly the same in every direction and from every location. No single place should be special. It's the guiding assumption that allows us to extrapolate what we see locally to the universe as a whole. The existence of a void as immense as the KBC void, with our galaxy sitting right near its center, seems to make our location very special indeed. It's as if we've been trying to understand the demographics of a vast city by only taking a census in a sparsely populated suburb. Our sample is heavily biased, and our conclusions about the entire metropolis could be dangerously skewed. The KBC void forces us to confront an unsettling possibility. What if our local, underdense environment is distorting our entire view of cosmic evolution? One of the most critical areas where this local void creates major complications is in our measurement of the Hubble constant the rate at which the universe is expanding. For decades, astronomers have used two primary methods to calculate this fundamental number. The first method builds a cosmic distance ladder by observing nearby stars and galaxies to calibrate distances and measure how fast they are receding from us. The second method looks back to the very early universe, studying the faint afterglow of the Big Bang, the cosmic microwave background, and using our understanding of physics to predict what the expansion rate should be today. The problem is, these two methods have persistently given different answers. They don't agree. This discrepancy, known as the Hubble tension, is one of the most significant unsolved problems in cosmology. Could the KBC void be a key piece of this puzzle? The logic goes like this. From our position inside a giant void, the gravitational landscape is unusual. The relative lack of matter in our immediate vicinity means there is less gravitational pull holding us back compared to regions outside the void, which are denser and have a stronger collective gravity. As a result, our local region of space may actually be expanding faster than the universe's true average expansion rate. Think of it like a boat on a river. If you're floating in a wide, slow-moving section, your speed relative to the riverbank might seem normal. But if you're suddenly swept into a narrow, fast-moving channel, your speed will increase dramatically. The local distance ladder measurements, which rely on observations of relatively nearby galaxies that are also inside this void, could be measuring this artificially heightened channel of expansion. Meanwhile, the cosmic microwave background measurement gives us the true average expansion rate of the entire river. If this interpretation is correct, the Hubble tension isn't a sign that our fundamental physics is wrong. It's a sign that we have failed to properly account for our unrepresentative location in the cosmos. Of course, the scientific community is not in full agreement about the KBC void. Its proposed size pushes the limits of what is considered plausible under our standard models of structure formation. Some cosmologists argue that such a vast underdensity is statistically very unlikely to exist. They suggest that potential observational biases or incomplete galaxy surveys could be making our local universe appear emptier than it truly is. The debate is ongoing, and it drives home a crucial point. Truly understanding the universe requires us to know exactly where we are within it. The search is on to map the cosmic structures on the largest possible scales with even greater precision, to confirm or refute the existence of this colossal void and fully understand its influence on our cosmic perspective. Whether it's ultimately confirmed or not, the KBC void hypothesis serves as a powerful reminder of a profound cosmic humility. Our view of the universe is not from a privileged, central position, nor is it from a completely average one. It is a view from a specific location with its own unique properties, and recognizing that bias is the first step towards seeing the true, grander picture. From the grand architecture of cosmic voids, we now turn our attention to a visitor, a mysterious traveler from the vast spaces between the stars that briefly swept through our own celestial neighborhood. In October 2017, astronomers at the University of Hawaii's Pan-STARRS telescope detected a faint point of light moving at a speed so blistering it could only mean one thing: this object was not from here. It was the first confirmed interstellar object ever observed within our solar system, and it was given the name Oumuamua, a Hawaiian term meaning a messenger from afar arriving first. This strange, cosmic vagabond immediately became a global sensation, not just for its origin, but for a series of bizarre properties that made it utterly unlike any asteroid or comet we had ever seen. The first major surprise was its shape. Based on the dramatic changes in its brightness as it tumbled through space, astronomers deduced that Oumuamua was highly elongated, perhaps 10 times as long as it was wide. Imagine a cosmic cigar or a flattened pancake tumbling end over end. This was a form factor never before observed in our solar system, where most objects are at least somewhat rounded by their own gravity. This peculiar shape immediately sparked questions about what kind of processes could create such an object in another star system. The second, and far more profound, mystery was its motion. As Oumuamua sped away from the Sun, astronomers carefully tracked its trajectory. They found that it was ever so slightly accelerating, deviating from the precise path that would be dictated by the Sun's gravity alone. Something was giving it an extra, non-gravitational push. For comets within our solar system, such behavior is common and is explained by outgassing. As a comet's icy surface is heated by the Sun, it vents jets of gas and dust, which act like a natural rocket engine, gently pushing the comet along. The catch with Oumuamua was that we never saw any of this activity. Our most powerful telescopes detected no coma, the fuzzy cloud of gas and dust that surrounds an active comet, and no telltale spectroscopic signature of water vapor or other gases being released. It was accelerating as if it were a comet, but it looked completely inert, like a bare, rocky asteroid. This paradox between its motion and its appearance launched a fierce and ongoing scientific debate. The leading natural explanation, championed by many astronomers, is that Oumuamua was indeed a comet, but a very exotic one. The theory suggests it could have been composed of very different ices than those in our solar system, such as solid nitrogen or solid hydrogen. When heated by the Sun, these ices could have turned directly from a solid to a gas in a process called sublimation, producing a faint, invisible jet of gas that provided the thrust without creating a visible dust cloud. Alternatively, Oumuamua could have been a porous, dusty aggregate, a so-called dust bunny on a cosmic scale, where the released gas could filter through its frothy structure without dragging dust grains along to become visible. These are plausible ideas, but they require Oumuamua to be made of materials that are either rare or behave in ways we haven't thoroughly observed, leaving an element of uncertainty that invited other, more speculative possibilities. The most famous of these alternative hypotheses came from Harvard astronomer Avi Loeb, who raised the provocative notion that Oumuamua could be an artifact of alien technology, perhaps a light sail, a vast, thin piece of machinery designed to be pushed by the radiation pressure from starlight. This idea, while captivating, was met with significant skepticism from the broader scientific community. Critics pointed out that while unusual, Oumuamua's properties were still within the realm of natural phenomena, even if we hadn't seen their exact like before. Invoking an extraterrestrial civilization is considered a hypothesis of last resort, one to be explored only after all natural explanations are exhausted. Furthermore, subsequent analysis showed that the amount of push from solar radiation pressure needed to explain the acceleration was remarkably high, requiring an object that was extremely thin and light, but also sturdy enough to survive an interstellar journey, a challenging set of properties for either a natural or an artificial object. Regardless of its ultimate nature, the mere existence of Oumuamua carries a profound implication for our understanding of the galaxy. Its detection suggests that interstellar space is not empty, but filled with a constant, drifting population of planetary rubble. Current estimates suggest that there could be thousands of such objects within the orbit of Neptune at any given time, each a silent traveler from a distant star. Every one of these objects is a fossil, a pristine sample from another planetary system that was likely flung out during the chaotic early stages of planet formation. By studying them, we can perform a kind of galactic geology without ever having to send a probe to another star. We can learn about the composition of other solar systems, the frequency of planetary ejections, and the fundamental building blocks that are shared across the Milky Way. Since Oumuamua, we have already detected a second interstellar object, Comet 2I/Borisov, which looked and behaved much more like a typical comet, suggesting there is a wide diversity of these interstellar nomads. Oumuamua was our first glimpse into this vast, invisible population, a single enigmatic data point that has permanently changed our perspective, revealing that the galaxy is a much more dynamic and interconnected place than we ever realized, constantly exchanging material and rewriting the story of its own formation one wandering rock at a time. While our solar system feels familiar, with its neatly aligned planets orbiting the Sun, the outer darkness beyond Neptune tells a very different and much more chaotic story. It's here, in the frigid, sunless expanse of the Kuiper Belt, that astronomers have noticed something deeply strange, a cluster of small, icy worlds whose orbits are all tilted and grouped in a way that defies simple gravitational explanation. They seem to be herded, their paths through the void orchestrated by an unseen conductor. This is the compelling mystery of Planet 9, a hypothetical world up to 10 times the mass of Earth, whose existence is inferred not by a direct glimpse, but by the ghostly tug it exerts on everything around it. The evidence for this hidden giant began to crystallize in 2014, when astronomers Chad Trujillo and Scott Shepard noted a peculiar clustering in the orbits of the most distant Kuiper Belt objects. These aren't your typical Pluto-like bodies. These are extreme trans-Neptunian objects with orbits that take them hundreds of times farther from the Sun than the Earth. What was so odd was that several of these objects shared similar orbital characteristics. Their points of closest approach to the Sun, known as perihelia, were all grouped together in space, and their orbits were all tilted at a similar angle relative to the plane of the solar system. For this to happen by random chance is statistically incredibly unlikely, like rolling a set of dice and having them all land on the same number multiple times in a row. The gravitational influence of the known giant planets, like Neptune, couldn't account for this grouping. There had to be something else out there, a massive perturber shepherding these distant objects into their strange, aligned dance. The case was powerfully advanced by Caltech astronomers Konstantin Batygin and Mike Brown, who conducted extensive simulations. They demonstrated that the gravitational pull of a single large planet on a distant, elongated orbit could naturally explain not only the orbital clustering, but also the existence of objects with orbits perpendicular to the solar system's plane, and even the peculiar, tilted orbit of a distant world called Sedna, which never comes close to the giant planets. The hypothetical Planet 9 in their model would be a super-Earth or a mini-Neptune with a mass between 5 and 10 times that of our own world. Its orbit would be immense, taking between 10,000 and 20,000 years to complete a single journey around the Sun. At its most distant, it would be over 1,000 times farther from the Sun than Earth is, lingering in a profound and perpetual twilight. This isn't a planet that simply reflects sunlight. It's a world that would be a native of the darkness, its presence betrayed only by the subtle ripples it creates in the fabric of our solar system. Finding this phantom world, however, is a monumental challenge that pushes the limits of modern astronomy. The primary obstacle is its incredible distance and expected faintness. At such vast removes, the Sun would appear as little more than an exceptionally bright star in its sky, providing almost no illumination. Any light reflected from its surface would be extraordinarily dim by the time it traveled back to our telescopes. Furthermore, we only have a rough idea of where to look. Pinpointing its exact location requires tracing back the gravitational influences on the known distant objects, a complex mathematical puzzle with a wide range of possible solutions. It's like trying to find a single specific car in a massive, planet-sized parking lot that's pitch black, and you only have a vague description of the neighborhood it might be parked in. Astronomers are using the world's most powerful telescopes, like the Subaru telescope in Hawaii, to conduct a painstaking, piece-by-piece survey of the most likely patches of sky. This process is slow and methodical, requiring them to compare images taken nights or weeks apart to look for any faint point of light that has moved against the backdrop of fixed stars. It is a grand, cosmic needle in a haystack search, but one with a potentially universe-altering prize at the end. The implications of actually discovering Planet 9 would be nothing short of revolutionary for our understanding of the solar system's history. Its very existence would solve one mystery while creating a host of fascinating new questions, the most pressing being, how did it get there? It is almost certainly too large to have formed in its current, distant orbit. The protoplanetary disk of gas and dust from which the planets coalesced was likely not massive enough that far out. This leads to two compelling scenarios for its origin. The first is that Planet 9 is an exiled giant, formed much closer to the Sun alongside Jupiter and Saturn. During the solar system's violent early youth, a gravitational tug-of-war between the young gas giants could have flung this world outward on a vast, eccentric orbit, where it settled in the distant reaches it inhabits today. The second, even more dramatic possibility is that Planet 9 is a captured alien. It may not have formed in our solar system at all, but could have been an interstellar rogue, a free-floating planet that was gravitationally captured by the Sun as it drifted by. This would mean our solar system has adopted a world from another star, a permanent immigrant from the galactic community. Either scenario paints a far more dynamic and chaotic picture of our solar system's infancy than the calm, orderly process we once imagined. It suggests that the outer solar system is a cosmic junkyard, littered with the remnants of planetary billiards and interstellar acquisitions, with a hidden king still ruling from the shadows. The discovery of Planet 9 would not just add a new world to our charts, it would fundamentally rewrite the story of our cosmic home, revealing a history of gravitational drama and interstellar exchange right on our own galactic doorstep. While we often picture the galaxy as a collection of stars, planets, and vast clouds of gas, there is another, invisible component weaving through it all, a pervasive force that sculpts the cosmos in ways we are only beginning to understand. This is the mystery of the Milky Way's magnetic field. Envision a complex, invisible web of magnetic lines of force, stretching for tens of thousands of light years, threading through every nebula, wrapping around every spiral arm, and extending far out into the galactic halo. This magnetic tapestry is not just a background feature. It is an active and dynamic player in the life cycle of the galaxy, influencing everything from the paths of high-energy cosmic rays to the very birth of new stars. Yet, for its profound importance, its origins and its grand-scale structure remain one of astrophysics' most intricate and compelling puzzles. So how do we even begin to study something we cannot see? The key lies in a property of light called polarization. As starlight travels through the vast clouds of interstellar dust that fill the galaxy, the dust grains are not randomly oriented. The galaxy's magnetic field causes these tiny, elongated particles to align themselves, much like iron filings aligning with the field of a bar magnet. When starlight encounters these aligned grains, they preferentially scatter the light waves that are oscillating in one particular direction. This process polarizes the light, meaning the light waves become oriented in a specific plane. By carefully measuring the polarization of starlight from millions of distant stars, astronomers can effectively trace the orientation of the magnetic field lines that the light encountered on its long journey to Earth. It's like reading a cosmic compass, where the starlight itself carries the imprint of the magnetic fields it has passed through. Another powerful tool for mapping this invisible architecture comes from radio astronomy. Electrons, spiraling at nearly the speed of light along these galactic magnetic field lines, emit a very specific type of radio wave known as synchrotron radiation. This emission is also polarized, and by analyzing it with giant radio telescopes, we can create detailed charts of the magnetic field's strength and direction in regions far from any stars. These complementary techniques, starlight polarization and synchrotron radio mapping, have together revealed a magnetic landscape of astonishing complexity. The field is not a simple, large-scale dipolar structure like Earth's. Instead, it appears to be a tangled mixture of an ordered, large-scale component that follows the spiral arms and a chaotic, turbulent component that resembles a cosmic magnetic storm churned up by supernova explosions and stellar winds. The influence of this magnetic web is both subtle and profound. Consider the journey of a cosmic ray, a high-energy proton or atomic nucleus racing across the galaxy at nearly the speed of light. These particles do not travel in straight lines. They are deflected and scrambled by the galaxy's magnetic fields, their paths twisted into a random walk that makes it nearly impossible to trace them back to their source. The magnetic field acts as a giant containment vessel, trapping these dangerous particles and preventing them from simply streaming out into intergalactic space. This is why our solar system is bathed in a relatively steady drizzle of cosmic radiation. The magnetic fields keep them confined within the galactic disk. Perhaps even more crucial is the role magnetism plays in the delicate dance of star formation. Giant molecular clouds, the stellar nurseries of the galaxy, are incredibly massive and dense. Left to gravity alone, these clouds would collapse catastrophically into stars, resulting in a brief, furious burst of star formation that would quickly consume all the available gas. But that is not what we observe. Star formation is a slow, inefficient process, and magnetic fields are a primary reason why. The fields penetrate these clouds, providing a form of internal support. The magnetic pressure pushes back against the relentless pull of gravity, acting as a cosmic brace that slows the collapse, allowing the cloud to fragment gradually and form stars over millions of years. Without this magnetic support, the galaxy would look radically different, its gas supply long since exhausted in a few frantic episodes of stellar birth. The magnetic field is the patient, regulating hand that ensures star formation is a sustained, multi-billion-year process, one that ultimately allowed for solar systems like our own to have the time to form and evolve. Despite understanding its effects, the fundamental question of how this vast magnetic field was generated in the first place remains wide open. The leading theory points to a process known as the galactic dynamo. The basic idea is that the motion of electrically conductive plasma within the galaxy's disk, the rotation of the galaxy itself, combined with the turbulent rising and falling of gas from supernovae, can amplify a small, initial, seed magnetic field and stretch it into the colossal structure we see today. It's analogous to a bicycle dynamo, where mechanical motion is converted into electrical current and a magnetic field. In the galactic version, the entire rotating disk of the galaxy acts as the dynamo, sustaining the magnetic field over billions of years. However, this theory has its own deep mystery. Where did the original seed field come from? Was it generated in the early universe, perhaps in the fractions of a second after the Big Bang, and then woven into the fabric of galaxies as they form? Or was it created later by the first generations of stars and galaxies, seeding the cosmos with magnetism that then spread and grew? The answer is still elusive, making the galactic magnetic field not just a feature of our Milky Way, but a fundamental and unresolved piece of the cosmic puzzle. But our cosmic inventory of mysteries doesn't end with what we can see or map. It extends down to the very atoms that make up the universe. one of the most persistent and fundamental puzzles in all of cosmology, is known simply as the lithium problem, and it deals with a discrepancy in the amount of a specific element found in the oldest stars of our galaxy. To understand why this is such a big deal, we have to rewind the cosmic clock all the way back to the universe's first few minutes, to an era known as Big Bang nucleosynthesis. In this incredibly hot, dense, and rapid phase after the Big Bang, the entire universe was a seething nuclear fusion reactor. Protons and neutrons collided and fused, creating the first atomic nuclei in existence, primarily hydrogen, a good amount of helium, and a tiny, tiny trace of lithium. For decades, our sophisticated models have calculated precisely how much of each element should have been forged in that primordial cauldron. For hydrogen and helium, the predictions match the observed abundances in the oldest stellar populations almost perfectly. It's a stunning triumph for the Big Bang theory, but for lithium, there's a major problem. The models tell us there should be about 3 times more lithium-7, the most common isotope, than what we actually measure in these ancient stars. This isn't a small rounding error. It's a factor of 3 discrepancy that has stubbornly resisted explanation for over 30 years. These ancient stars act as cosmic time capsules. They formed from nearly pristine gas that had been contaminated by very few previous generations of stars, so their chemical composition gives us a direct window into the elemental makeup of the early universe. When astronomers use powerful spectrographs to analyze the light from these stellar relics, they can see the distinct absorption lines of lithium in their atmospheres. And time and again, the measured value comes up short. It's as if someone went through the early universe and secretly threw away 2/3 of its lithium supply. This presents a profound challenge because Big Bang nucleosynthesis is one of the foundational pillars of modern cosmology. If our understanding of those first few minutes is even slightly incorrect, it could have ripple effects through our entire model of cosmic evolution. So, where did the lithium go? Or was it never made in the expected amounts to begin with? Scientists have pursued 2 broad paths to solve this puzzle. The first path involves questioning our understanding of the physics of the early universe itself. Perhaps our standard model of particle physics is incomplete, and some unknown type of particle was present in those first moments that interacted with the nascent nuclei, altering the nuclear reaction rates. One candidate is a type of hypothetical particle known as a supersymmetric particle, which could have decayed and injected extra neutrons into the mix, changing the delicate balance of fusion that produces lithium. Another radical idea is that the density of ordinary matter in the early universe was not perfectly uniform, and these small fluctuations could have led to pockets where lithium was produced less efficiently. These are fascinating possibilities, but they require tweaking our most fundamental theories, which is a step physicists are hesitant to take without overwhelming evidence. The second, and currently more popular, path looks for an astrophysical solution within the stars themselves. Maybe the Big Bang did produce the correct amount of lithium, but something destroyed it before we could observe it in these ancient stars. Stars are, after all, complex engines, and their interiors can process and transmute elements. The surface of an old star might not reflect the exact composition of the gas from which it formed. One compelling theory suggests that as these ancient stars formed and settled down, they went through a prolonged pre-main sequence phase where they were largely convective. This means that the material at their surface could have been cycled down into the hotter interior, where temperatures are high enough to burn lithium. In this scenario, the star acts like a cosmic blender, dragging its surface lithium down to a depth where it is destroyed by nuclear fusion, effectively depleting the visible reservoir. Another possibility involves the bombardment of the stellar atmosphere by cosmic rays, which could spallate or break apart the fragile lithium nuclei. While these astrophysical explanations are elegant, they also face their own challenges in matching the detailed observations across different types of ancient stars. The lithium problem endures precisely because no single solution has managed to fully and convincingly reconcile the pristine predictions of the Big Bang with the stubborn evidence written in the light of our galaxy's oldest suns. It stands as a quiet but persistent reminder that even our most successful cosmic theories might still be missing a crucial piece of the puzzle. Leaving behind the subtle atomic puzzles of the early universe, we now encounter a phenomenon of raw, unbridled stellar power. Picture a star not as a fixed point of light in a familiar constellation, but as a cosmic cannonball, hurtling through the void at a staggering pace, blazing a path of destruction and creation through the galactic medium. These are runaway stars, and they are some of the most dynamic and visually spectacular objects in the Milky Way. One of the most famous examples is Zeta Ophiuchi, a brilliant blue giant that is currently racing through space at an incredible velocity of around 30,000 kilometers per hour. If you could see its motion in real time, it would look less like a star and more like a ship plowing through a celestial ocean at breakneck speed. The origin of such tremendous stellar velocity typically points to one of two incredibly violent scenarios. The first is a supernova kick. Imagine a pair of stars, a binary system, locked in a mutual gravitational dance. One of the stars is more massive and lives its life quickly, ending in a cataclysmic supernova explosion. When a supernova occurs, it is rarely perfectly symmetrical. The titanic blast can eject material in one direction more than another, effectively kicking the remaining stellar core, now a neutron star, like a rocket. Due to Newton's third law, the binary companion that survived the blast receives an equally powerful kick in the opposite direction. It is suddenly freed from the gravitational bond that held it and flung into space at its original orbital velocity plus the kick from the explosion. It's the cosmic equivalent of swinging a ball on a string and then suddenly letting go, the ball goes flying. Zeta Ophiuchi is a prime candidate for this kind of history. Astronomers suspect it was once the companion to an even more massive star that blew up, catapulting it on its current high-speed journey. The second common mechanism involves gravitational billiards within densely packed star clusters. In the core of a globular cluster or a young open cluster, stars are crammed together in a relatively small volume. Close gravitational encounters between stars are common. When two binary star systems pass near each other, the complex gravitational interactions can sometimes fling one of the stars out of the cluster entirely, like a slingshot, at a tremendous speed. In some cases, a single star can have a very close encounter with a binary system, getting a massive gravitational boost that sends it careening into the void. These runaway stars are the survivors of stellar traffic accidents, ejected from their crowded birthplace to wander the galaxy alone. The most stunning and immediate evidence of a runaway star's journey is not the star itself, but the magnificent structure it creates in the space ahead of it, a bow shock. As the star rockets through the galaxy, it doesn't travel through a perfect vacuum. The interstellar medium is filled with tenuous clouds of gas and dust. The star emits a powerful stream of particles known as a stellar wind, which rams into this ambient material. The interaction is very much like the wave that forms at the bow of a speedboat moving through water. The stellar wind, moving at millions of kilometers per hour, collides with the nearly stationary interstellar gas, compressing and heating it to brilliant incandescence. This creates a glowing, arc-shaped wall of material that shines in infrared light, often visible to space telescopes like NASA's Spitzer and WISE. The bow shock around Zeta Ophiuchi is a particularly spectacular example, a vast, asymmetric crescent of heated dust and gas that stretches for several light years, a permanent sonic boom written in light and radiation, announcing the star's passage for all the cosmos to see. Studying these runaway stars and their bow shocks provides astronomers with a unique form of cosmic diagnostics. The shape, size, and structure of the bow shock tell a detailed story about the conditions of the interstellar medium the star is plowing through. A smooth, symmetrical bow shock suggests the star is moving through a region of uniform density. A lumpy, distorted shock wave, on the other hand, indicates it is encountering a turbulent and clumpy environment. By analyzing the light from these shocks, we can measure the composition and density of the interstellar gas in different parts of the galaxy, creating a map of the galactic ecosystem that would be difficult to obtain by other means. Furthermore, the runaway stars themselves are invaluable probes. They act as tracers, their paths across the sky allowing us to trace them backward, like following a comet's tail in reverse, to pinpoint their origin. This reverse engineering can lead us directly back to the stellar nursery or star cluster that gave them birth, offering profound insights into the conditions and dynamics within those violent, crowded environments. In this way, these lonely, high-velocity travelers are not just fugitives. They are messengers, carrying with them the untold story of the violent events that launched them on their epic journeys across the Milky Way. But what if the entire structure of our galaxy, the very shape we see today, was forged in a single, monumental collision in the ancient past? This brings us to a discovery that has completely rewritten the early history of the Milky Way, an event preserved not in the stars themselves, but in the unique patterns of their motion. Thanks to the incredible precision of the European Space Agency's Gaia Space Observatory, which has been meticulously mapping the positions, distances, and velocities of nearly 2 billion stars, we have uncovered the ghostly remains of a long-dead galaxy lurking within our own. This ancient galactic immigrant is nicknamed the Gaia Sausage, a name that comes not from its visual appearance, but from its distinct, sausage-like shape when plotted on a graph of stellar velocities. It represents the debris of a dwarf galaxy that smashed into the infant Milky Way some 8 to 10 billion years ago, a collision so violent and transformative that it fundamentally built the galaxy we call home today. The story of this discovery is a triumph of modern data science. The Gaia spacecraft doesn't just tell us where stars are, it tells us how they are moving. When astronomers began analyzing the velocities of millions of stars in the galaxy's halo, the vast, sparse sphere of ancient stars that envelops the main disk, they noticed something extraordinary. A huge population of these stars weren't moving in random, swirling orbits. Instead, they were streaming along highly elongated radial paths, plunging dramatically toward the galactic center, and then swinging far out into the halo again. When you plot the star's velocities relative to the galactic center, this specific population clusters into a distinctive, elongated shape that resembles a sausage or a football. This peculiar motion is the celestial fingerprint of a galactic merger. These stars are the orphan remnants of the dwarf galaxy, their orbits preserving the memory of the colossal impact that tore their original home apart. The scale of this cataclysm is difficult to overstate. The Sausage Galaxy, whose formal name is the Gaia Enceladus Galaxy, was no minor speck. Before the collision, it was a substantial dwarf galaxy, likely containing several hundred million stars, and perhaps as much as 10% of the Milky Way's own mass at the time. This was not a gentle merging of clouds. It was a head-on, catastrophic assault. The gravitational violence of the impact would have been staggering, shredding the smaller galaxy into a tidal stream of stars that was then woven into the fabric of the Milky Way's halo. But the collision did far more than just add stars to the halo. It fundamentally reshaped the Milky Way's very architecture. Prior to this merger, our galaxy was likely a much thinner, more delicate structure. The immense energy released by the Gaia Enceladus impact sent powerful shockwaves through the nascent galactic disk, puffing it up and stirring it violently. This is the event that scientists now believe was primarily responsible for creating the Milky Way's thick disk, that component of our galaxy which consists of older stars that orbit in a wider, more inflated plane compared to the thin disk where our Sun resides. The collision essentially battered the young Milky Way, thickening its disk and contributing a significant fraction of the stars we now find in both the thick disk and the inner halo. This revelation has turned our understanding of galactic evolution on its head. We once pictured galaxy growth as a slow, steady process of accretion, like a snowball gently rolling and gathering more snow. The Gaia sausage tells a story of punctuated equilibrium, where sudden, violent events dictate the course of a galaxy's life. The merger with Gaia Enceladus was the defining moment in the Milky Way's adolescence, a growth spurt triggered by a galactic cannibalism event that set its structure for billions of years to come. By studying the chemical composition of the sausage stars, astronomers have confirmed their foreign origin. These stars are typically older and contain fewer heavy elements, what astronomers call metals, than stars born in the primordial Milky Way. This makes perfect sense, as the smaller dwarf galaxy would have had a shorter, less productive history of star formation and supernova, leaving its stellar population more pristine and metal-poor. The identification of the Gaia sausage is more than just an archaeological dig into our galaxy's past. It is a template for understanding the universe. It shows us that the halos of large spiral galaxies are not just random collections of old stars, but are layered archives of past mergers. Each stellar stream, each cluster of stars with unique kinematics, is a chapter in a violent autobiography. The Gaia mission continues to sift through the motions of the stellar population, revealing other, smaller streams and remnants, painting a picture of a galaxy that has been assembled from countless smaller pieces over cosmic time. The sausage is simply the largest and most dramatic of these chapters yet read. It stands as a permanent monument to a formative trauma, evidence that the majestic spiral we see today was forged in the fire of a colossal impact, a cosmic union that forever altered the destiny of our galactic home. From the violent history of galactic mergers, we now turn to the beautiful and ongoing process of cosmic creation, where vast clouds of gas and dust collapse under their own gravity to give birth to new suns. A perfect example of this breathtaking, yet deeply mysterious, process is the Cat's Paw Nebula, a sprawling stellar nursery located about 5,500 light-years away in the constellation Scorpius. In visible light images, it appears as a vast, glowing red cloud, its curved, paw-pad-like bubbles sculpted by the intense radiation from the brilliant young stars buried within. This nebula is not just a pretty picture, it is a dynamic and chaotic laboratory, a place where the fundamental rules of star formation are being written, and where some of the most stubborn questions in astronomy remain unanswered. One of the most immediate puzzles is why stars almost always seem to form in groups, in these vast clusters that can contain anything from a few dozen to many thousands of members. The Cat's Paw Nebula is a quintessential example, hosting a rich, open cluster of infant stars. The prevailing theory points back to the sheer scale and dynamics of the giant molecular clouds that serve as their birthplaces. These clouds are not smooth and uniform. They are incredibly turbulent, filled with complex networks of filaments and dense knots, all swirling under the influence of their own gravity and magnetic fields. When a particularly dense region within this cloud reaches a critical point, it begins to collapse. But this collapse is not an isolated event. The gravitational instability can trigger a chain reaction, causing neighboring dense clumps to also succumb to gravity in a relatively short period of time. It's a cosmic domino effect, resulting in a whole population of stars being born together from the same parent cloud. Furthermore, once the first massive stars ignite, their powerful stellar winds and radiation can compress the surrounding gas, triggering a second wave of star formation in a shell around them, a process known as triggered star formation. So, the cluster we see in the cat's paw is likely the product of both spontaneous gravitational collapse and the disruptive, creative influence of its own most massive children. Yet, even within these clusters, the final outcome for any individual star seems to follow a surprisingly strict and universal rule, a cosmic statistic known as the initial mass function. This is not a law of physics in the traditional sense, but rather a profound observational pattern that describes how stellar mass is distributed at birth. Simply put, when a giant cloud forms stars, it produces a vast number of low-mass stars, a smaller number of intermediate-mass stars like our Sun, and only a very few truly massive, brilliant, but short-lived giants. For every single star with the mass of 50 suns, a stellar nursery like the cat's paw will form tens of thousands of stars smaller than our own Sun. This distribution appears to be remarkably consistent across our galaxy, and even in other galaxies, regardless of the specific environment. This is deeply puzzling. Why should the process of star formation, which begins in the chaotic, turbulent maelstrom of a molecular cloud, result in such a predictable and repeatable outcome? What physical mechanism decides that a particular collapsing clump of gas will become a red dwarf, a sun-like star, or a colossal blue giant? The answer is far from settled, and it lies at the heart of the star formation mystery. Gravity alone would tend to create more massive clumps, but other forces are at work to resist it. Turbulence within the cloud can provide support, breaking up large, collapsing regions into smaller fragments, which would naturally lead to a preference for lower-mass stars. Magnetic fields also play a crucial role, providing an additional form of pressure that can slow or even halt the collapse of a core, effectively setting a limit on how much mass it can gather. The current frontier of research involves incredibly complex computer simulations that try to model all these factors simultaneously: gravity, turbulence, magnetic fields, and later, the feedback from the stars themselves. These simulations are getting closer to reproducing the observed initial mass function, but they haven't yet pinpointed a single, simple reason for its remarkable universality. It suggests that there is a fundamental, self-regulating balance in the physics of collapsing gas clouds, a balance that consistently favors the creation of small, dim stars over brilliant, heavyweight ones. This balance is powerfully influenced by the very stars that are born, especially the most massive ones. This brings us to the complex and paradoxical role of stellar feedback. The massive stars within a nebula like the cat's paw are both creators and destroyers. On one hand, their intense ultraviolet radiation and powerful stellar winds can slam into the surrounding molecular cloud, compressing it and triggering the formation of a new generation of stars, as mentioned before. They essentially build their own siblings by pushing on the cosmic gas. The magnificent, glowing bubbles in the cat's paw nebula are direct evidence of this process. They are the shock fronts where this energetic output is plowing into the cooler, ambient material. However, this creative force has a destructive dark side. The same radiation and winds that can trigger star formation also carry enormous energy. Over time, they begin to violently heat and disperse the very gas cloud that gave them birth. They blow vast cavities in the nebula, and once this gas is heated and scattered back into the interstellar medium, it can no longer collapse to form new stars. The massive stars are essentially evaporating their own nursery, bringing the era of star formation in that region to an abrupt and decisive end. In the cat's paw nebula, we are likely witnessing this pivotal phase. Some areas are still actively forming stars, while others have been cleared out by the brilliant, massive stars, their gas and dust blown away to perhaps one day collapse elsewhere and begin the cycle all over again. This feedback loop is a critical regulator, ensuring that star formation is a slow and inefficient process across the galaxy, rather than a runaway event that would consume all the available gas in a cosmic blink of an eye. It is a dramatic story of creation and destruction, written in the glowing gas and dark dust of one of the Milky Way's most iconic stellar nurseries. Yet the staggering power of a magnetar pales in comparison to a discovery that truly tests the limits of our imagination, a place where the very fabric of reality seems to break down. This is our 17th phenomenon, the confounding nature of a black hole's event horizon and the bizarre paradox that may lie at its heart. For decades, we've understood the event horizon as the ultimate point of no return, a one-way boundary in spacetime from which not even light can escape. It's the black hole's defining feature, the invisible surface that shrouds the singularity, a point of infinite density where our known laws of physics simply cease to function. This classical picture, born from Einstein's theory of general relativity, is elegant and terrifying in its finality. Anything that crosses this threshold is lost to our universe forever, its information seemingly erased from existence as it is crushed into the singularity. However, this classic view comes into direct, violent conflict with another cornerstone of modern physics, quantum mechanics. In the quantum world, information is never truly lost. The quantum state of a system, the specific configuration of all its particles, must be preserved in principle. You could, theoretically, reverse time and see how that system evolved. This is known as unitarity, a fundamental tenet of quantum theory. But what happens when you throw a book into a black hole? According to general relativity, the book crosses the event horizon, is torn apart, and its constituent particles are added to the mass of the singularity. The information contained in the words on those pages is gone, obliterated. This creates the famous black hole information paradox, a profound contradiction between our two most successful descriptions of the universe. How can the information about that book be both permanently lost inside the black hole and also fundamentally preserved according to the rules of quantum mechanics? This isn't just a philosophical puzzle. It points to a fundamental flaw in our understanding, a place where either general relativity, quantum mechanics, or both must be amended. One of the most intriguing potential solutions to this paradox was proposed by the renowned physicist Stephen Hawking. He suggested that black holes are not entirely black. Due to weird quantum effects occurring just outside the event horizon, black holes should slowly radiate energy, losing mass over time. This radiation, now known as Hawking radiation, arises from the spontaneous creation of particle-antiparticle pairs from the quantum vacuum. Normally, these pairs would annihilate each other almost instantly, but if this creation happens right at the event horizon, one particle can fall in while the other escapes, stealing a tiny amount of the black hole's energy. The critical point is that Hawking radiation is thermal. It's random and featureless, carrying no information about what fell into the black hole. So, if a black hole eventually evaporates completely through this process, radiating away all its mass as random heat, what happened to the information of the book? It seems to be lost forever, deepening the paradox rather than solving it. This has led to some truly mind-bending modern hypotheses. One compelling idea is the fuzzball proposal from string theory. It suggests that what we think of as a black hole with a sharp event horizon and a central singularity is actually a mistake. Instead, the entire interior of the black hole is filled with a giant, tangled ball of strings the fundamental vibrating loops that string theory proposes make up all particles. This fuzzball has no sharp boundary or central point of infinite density. The information of anything that falls in isn't concentrated at a singularity, but becomes intricately woven into the complex vibrations of this giant stringy object. In this view, there is no information paradox because there is no classical event horizon where information is lost. It's all just stored in the fuzzball structure, and it could, in principle, be decoded from the Hawking radiation, though in an incredibly complex way. Another radical concept is the firewall hypothesis. This proposes that to preserve quantum information, the event horizon cannot be the smooth, uneventful space that general relativity predicts. Instead, it might be a literal wall of blazing high-energy particles, a firewall. As an astronaut approaches the horizon, instead of crossing it peacefully, they would be instantly incinerated by this wall of energy. This violent solution would resolve the paradox by ensuring that information never actually enters the black hole. It is smeared and encoded onto the fiery surface of the horizon. While this saves the principle of information conservation, it blatantly violates the core idea of general relativity, which states that an observer falling through the event horizon should feel no special forces, a principle known as the no-drama scenario. The firewall idea is so controversial because it forces physicists to choose which fundamental principle they are willing to abandon, the smoothness of spacetime or the preservation of quantum information. Ultimately, the black hole information paradox is more than just a theoretical debate. It is a powerful engine for discovery. It is forcing us to develop a theory of quantum gravity, a framework that can successfully merge the large-scale world of gravity and spacetime with the small-scale world of quantum particles. The event horizon is the ultimate laboratory for this, a place where both theories must apply simultaneously. Whether the answer lies in fuzzballs, firewalls, holographic principles where information is stored on the surface, or something even more extraordinary, resolving this paradox will undoubtedly lead to a revolution in physics as profound as those sparked by relativity and quantum mechanics themselves. It reminds us that our universe's greatest mysteries are not always found in distant nebulae or wandering comets, but can be hidden in the profound, unsettling implications of a simple, dark boundary from which nothing is supposed to return. Yet as we contemplate the conditions that gave rise to our own existence, we are led to a broader and more profound question. Is life a common occurrence throughout the Milky Way, or is our planet's position uniquely suited for such a complex experiment? This brings us to the fascinating concept of the Galactic Habitable Zone, a theory suggesting that not all neighborhoods within our galaxy are equally welcoming to life. Much like the habitable zone around a star, the so-called Goldilocks region, where temperatures are just right for liquid water, the galaxy itself may have a sweet spot, a radial band where conditions are most favorable for the emergence and long-term survival of complex biological systems. Our own solar system, it turns out, resides in what appears to be an exceptionally privileged location, about 27,000 light-years from the galactic center, nestled within a relatively quiet spiral arm. Several critical factors converge to make this region so hospitable. The first is the availability of the necessary building blocks. The universe began with only the lightest elements, hydrogen, helium, and a trace of lithium. Every heavier element essential for life, the carbon in our cells, the oxygen we breathe, the iron in our blood, was forged in the nuclear furnaces of stars and scattered across the galaxy by violent supernova explosions. This process of chemical enrichment took time. Regions too close to the galactic center formed stars so early and so rapidly that the interstellar medium was not yet sufficiently seeded with these heavier elements, or metals, to form rocky, terrestrial planets like Earth. Conversely, the outermost reaches of the galaxy have remained relatively pristine and metal-poor, with fewer of the resources needed to build a solid world. Our position in the galaxy's mid-region represents a perfect balance, a place where multiple generations of stars have lived and died, enriching the cosmic environment with just the right abundance of metals to allow for the formation of our solar system some 4.6 billion years ago. But having the right ingredients is only part of the story. Life also requires a stable and relatively peaceful environment in which to evolve over billions of years. This is where the second major factor comes into play, the threat of sterilizing radiation. The inner regions of the Milky Way, especially the crowded galactic bulge, are a dangerous and volatile place. Stars are packed together much more densely, increasing the probability of gravitational disruptions that could fling comets and asteroids into planetary systems. More critically, the frequency of nearby supernova explosions is far higher. A close supernova, within about 30 light-years, would bathe any orbiting planet in a torrent of X-rays and gamma rays, potentially stripping away its atmosphere and irradiating its surface. Furthermore, the supermassive black hole at the galactic center, Sagittarius A star, occasionally unleashes powerful outbursts of energy that could have similarly devastating effects across vast distances. Our location in the galactic suburbs provides a vital buffer from this constant cosmic turmoil, offering a quieter, more stable stage for the slow, intricate dance of evolution to unfold. However, the concept of a galactic habitable zone is not without its complexities and controversies. Some scientists argue that while the inner galaxy is undoubtedly more hazardous, it might not be completely sterile. Life, once it takes hold, can be remarkably tenacious. It is conceivable that on moons or planets shielded by thick ice sheets or deep oceans, microbial life could survive even in more hostile environments. Moreover, the definition of habitable is inherently biased toward life as we know it. We are carbon-based, water-dependent organisms, but it is possible that entirely different forms of biochemistry could arise under conditions we would consider extreme. The Galactic Habitable Zone, then, might be more accurately described as the complex life zone, a region where the conditions are most favorable for the evolution of large, multicellular, and technologically advanced species like ourselves. This perspective also raises the tantalizing possibility of temporal variation. The galactic habitable zone is not a static ring. It evolves over time. In the early galaxy, the safe zone was likely much narrower, confined to a thin band far from the violent center. As the galaxy aged and the interstellar medium became more uniformly enriched with metals, this habitable region may have expanded outward. Our solar system formed at a time when the galaxy had reached a certain level of maturity, a golden era for planet building. This introduces the idea that there could be a galactic habitable age, as well as a zone, a specific window in cosmic history, when the probability for complex life is at its peak. So, when we look up at the Milky Way, we are not just observing our home in space, but also in time, occupying a fortunate moment in the galaxy's multi-billion-year story. The evidence gathered so far suggests that while there may be vast swaths of the galaxy where simple life could potentially persist, the specific conditions required for the long-term, stable development of complex civilizations might be a much rarer and more precious cosmic commodity, making our own pale blue dot an even more remarkable and perhaps singular haven in the grand spiral. Leaving the theoretical boundaries of black holes and the galactic habitable zone, we come to a different kind of puzzle, one that challenges our understanding of the very building blocks of the cosmos. This is the missing satellite problem, a stubborn discrepancy that pits our most sophisticated computer simulations of the universe against the hard, observational evidence we gather from our own galactic backyard. According to the wildly successful lambda cold dark matter model, which is our standard recipe for the universe, the Milky Way should be swarming with hundreds of small, dark matter-dominated dwarf galaxies in orbit around it. These tiny galactic satellites are predicted to be the leftover crumbs from the hierarchical assembly of our galaxy, the first and most ancient structures to form in the cosmos. Yet, when we look up, we only find a few dozen. It's as if our cosmic blueprint calls for a vast, bustling archipelago of islands around a continent. But when we step outside, we only see a handful of small, isolated rocks. This glaring mismatch forces us to ask a critical question. Is our theory of dark matter fundamentally flawed, or are we simply not seeing the full picture? The root of this problem lies in the nature of dark matter itself. In the standard model, dark matter is cold, meaning its particles move relatively slowly. This allows it to clump together readily under gravity, starting with tiny halos that then merge to form larger and larger structures. Cosmological simulations that model this process with immense supercomputers consistently produce a stunning result. Thousands of these small, dark matter clumps should have survived the formation of a galaxy like the Milky Way, each one massive enough to host its own small collection of stars, a dwarf galaxy. The sheer number of these predicted satellites is a direct consequence of the dark matter paradigm. So, when our actual census of Milky Way satellites comes up hundreds short, it strikes at the heart of our most foundational cosmological model. For a long time, it was possible to argue that our telescopes just weren't sensitive enough to see the faintest of these objects. However, as our surveys have grown more powerful, like the groundbreaking Sloan Digital Sky Survey and the more recent Dark Energy Camera, we have discovered many more ultra-faint dwarfs, but we are still nowhere close to the predicted population. The gap, while narrowed, remains a chasm. One of the most compelling potential solutions to this mystery involves tweaking the properties of dark matter. What if it isn't perfectly cold, but is instead slightly warm? Warm dark matter would consist of particles that are much lighter and faster moving. This slight increase in velocity would have a profound effect in the early universe, smoothing out the smallest scales of density fluctuations. It would suppress the formation of the very tiniest dark matter halos, resulting in a much smaller number of dwarf galaxies today, a number that could potentially align much better with our observations. While an attractive idea, the warm dark matter hypothesis is not without its own challenges. It must still account for the large-scale structure of the universe, which is exquisitely matched by the cold dark matter model. Furthermore, it would predict that the dwarf galaxies we do see should all have a similar, relatively large minimum mass, which is something astronomers are actively testing by studying the internal dynamics of these faint systems. Another promising avenue doesn't change dark matter at all, but instead focuses on the complex and destructive relationship between these small galaxies and their massive host. The reality is that living in the gravitational sphere of a giant like the Milky Way is a dangerous proposition for a dwarf galaxy. As these satellites orbit, they are subjected to intense tidal forces, the same kind of gravitational stretching that is currently tearing apart the Sagittarius dwarf. This process can strip away a dwarf galaxy's stars, and even more effectively, its dark matter halo, literally dissolving it over billions of years. Even more impactful is the effect of cosmic reionization. In the universe's first billion years, the first stars and galaxies flooded the cosmos with intense ultraviolet radiation, heating the hydrogen gas throughout space. This made it much more difficult for gas to cool and collapse inside the smallest dark matter halos, effectively shutting down their ability to form stars. A vast population of these dark halos could still be out there, completely invisible to our telescopes because they never managed to light up with stars in the first place. That would be made of pure dark matter, ghost satellites orbiting our galaxy in profound and undetectable darkness. This leads us to the most observationally driven solution, that we simply haven't found all the satellites yet because they are incredibly difficult to see. The faintest dwarf galaxies we have discovered are so dim that they were overlooked for decades, their sparse collection of stars blending seamlessly into the background of the Milky Way's own stellar halo. Finding them requires painstakingly scanning the sky and looking for subtle statistical overdensities of stars that are all moving together through space. Our current surveys, as powerful as they are still limited. They struggle to probe the low surface brightness universe, and they are often hampered by interstellar dust in the galactic plane. The next generation of observatories, like the Vera C. Rubin Observatory, promises to revolutionize this search. With its enormous mirror and massive digital camera, it will scan the entire visible sky with unprecedented depth and sensitivity, potentially uncovering hundreds of these ultra-faint dwarfs. The ultimate resolution to the missing satellite problem may therefore be a combination of all these factors. Some halos were suppressed by warm dark matter, others were stripped and destroyed by tidal forces, many were prevented from ever forming stars by reionization, and a significant population are simply waiting, just beyond the limit of our current vision, to be discovered. This cosmic detective story is far from over, and its conclusion will tell us not only how many companions our galaxy truly has, but will also place fundamental constraints on the nature of the dark matter that shapes the entire universe. But while the great structures of the galaxy present one scale of mystery, the subtle, unaccounted-for drift of a human-made object presents another. For decades, a quiet, persistent anomaly haunted the minds of deep space navigators, a tiny but measurable deviation in the paths of two robotic pioneers that seemed to defy our understanding of orbital mechanics. This is the story of the Pioneer anomaly, a ghostly tug that acted upon the Pioneer 10 and Pioneer 11 spacecraft as they journeyed into the abyss beyond Saturn. These intrepid probes, after completing their historic reconnaissance of the outer planets, were destined to become the first human artifacts to leave our solar system. As they sped toward the stars, scientists meticulously tracked their trajectories using the Doppler shift of their radio signals. By measuring the tiny changes in the frequency of these signals, they could calculate the probe's velocity with incredible precision. And that's when they found it, and constant sunward deceleration, a tiny but unrelenting pull back toward the sun that amounted to barely 10 billionths of a meter per second squared. It was a force equivalent to a single grain of sand resting in the palm of your hand, but over the vast distances of space and the years of travel, this minuscule effect accumulated into a navigational discrepancy of thousands of kilometers, a deviation that the standard models of gravity, accounting for the pull of every known planet and object, could not explain. The implications of such a consistent, unexplained force were profound. Could it be a sign of new physics? Theorists leaped at the puzzle, proposing a host of exotic explanations. Some suggested it was evidence of dark matter exerting a local gravitational drag within our solar system. Others proposed modifications to Einstein's theory of gravity itself, tweaking the laws on very large scales or in regions of extremely weak gravitational fields. The idea that our most fundamental understanding of gravity might be subtly incorrect was both thrilling and disconcerting, suggesting that Pioneer was revealing a crack in the foundation of modern physics. For nearly 20 years, the anomaly festered as an open case, a constant reminder of the universe's capacity to surprise us, even with the technology we had sent out from our own backyard. The ultimate resolution, however, turned out to be a masterclass in engineering humility and the relentless pursuit of a systematic explanation. A dedicated team of researchers, led by Slava Turashev, embarked on a monumental digital archaeology project. They painstakingly recovered decades-old data from archaic formats, tracked down original engineering documents, and even tracked the blueprints for the spacecraft's construction. Their breakthrough came from a meticulous analysis of a factor that had been initially considered too insignificant: heat. The Pioneer spacecraft were powered by radioisotope thermoelectric generators, or RTG, which produced electricity from the natural decay of plutonium. This process also generated a substantial amount of waste heat. The spacecraft themselves were asymmetric. The large, parabolic dish antenna acted as a shield, reflecting a large portion of this thermal radiation forward toward the front of the probe. According to the basic laws of physics, every photon of this infrared radiation carries a tiny amount of momentum. When that photon is emitted in one direction, it gives the spacecraft a minuscule push in the opposite direction. The team realized that the net effect of all this heat, radiating preferentially from the back of the spacecraft and bouncing off the large antenna, was creating a very slight but very constant recoil force pushing back toward the sun, exactly mimicking the signature of an anomalous deceleration. Through exhaustive computer modeling that accounted for the precise thermal profile of every component on the spacecraft, they were able to show that this thermal recoil force accounted for the vast majority of the mysterious Pioneer drift. While the thermal explanation has largely closed the book on the Pioneer anomaly for most of the scientific community, a whisper of uncertainty remains for some. The match between the model and the observed data is incredibly good, but perhaps not perfect, leaving a tiny residual effect that could, in principle, still point towards something new. More importantly, the entire decades-long episode serves as a crucial lesson for the future of deep space exploration. The need for exquisitely precise navigation has never been greater. Our modern missions, from the Voyagers at the edge of interstellar space to the New Horizons probe that flew past Pluto, rely on knowing their position and velocity with an accuracy that would have been unimaginable in the Pioneer era. An unaccounted for acceleration, even one as small as what plagued Pioneer, could mean the difference between a perfect flyby and missing a distant, frozen world entirely. The legacy of the Pioneer anomaly is therefore not a failed mystery, but a successful refinement of our process. It forced us to look more critically at our own engineering, to understand the subtle interactions between a spacecraft and its environment, and to build ever more sophisticated models that account for every conceivable non-gravitational force. It stands as a testament to the fact that sometimes the most intriguing cosmic puzzles are not found in the hearts of distant galaxies, but in the precise, patient analysis of the tiny whispers of data from the ambassadors we have sent into the void. As our solar system journeys through the Milky Way, it does so with a grand and rhythmic cadence, tracing a vast orbit that takes roughly 225 to 250 million years to complete a single circuit around the galactic core. This immense span of time defines what astronomers call a galactic year, a cosmic heartbeat that dwarfs all of human history. To put this scale into perspective, since the dinosaurs went extinct 66 million years ago, we have completed less than a third of a single galactic orbit. This slow, celestial waltz is not a perfectly smooth journey, however, and some scientists propose that the regular changes in our galactic environment as we travel could have a direct and dramatic impact on our planet's biosphere, potentially holding the key to one of paleontology's greatest mysteries, the periodic rhythm of mass extinctions. The underlying theory is as elegant as it is unsettling. As our sun travels its path, it doesn't move in isolation. It bobs up and down through the plane of the galactic disk, and most critically, it periodically passes through the galaxy's dense spiral arms. These arms are not solid structures, but rather waves of heightened density, regions where the concentration of stars, gas, and dust is significantly greater than in the inter-arm regions. It is hypothesized that each time our solar system enters one of these crowded spiral arms, the increased gravitational perturbation from all this extra mass disturbs the distant reservoir of icy bodies at the very edge of our solar system, the Oort cloud. This vast, spherical shell of frozen remnants is thought to extend nearly a light year from the Sun, and it is held only by the faintest gravitational tether. A significant gravitational nudge, the theory suggests, could dislodge a large number of these icy bodies, sending them plummeting inward toward the Sun in a dramatic increase in comet activity, an event known as a comet shower. If just a small fraction of these comets were to cross Earth's orbit, the resulting impacts would be catastrophic, injecting enough dust and vaporized rock into the atmosphere to trigger a global winter, collapse food chains, and cause a mass extinction. The evidence for this idea comes from the geological record itself. For decades, paleontologists have analyzed the fossil record and identified a pattern suggesting that major extinction events may not be entirely random. Some studies have pointed to a possible periodicity, with severe biodiversity crises occurring approximately every 26 to 30 million years. Intriguingly, this time frame is on the same order as the estimated time it takes for our solar system to oscillate vertically through the galactic plane, a motion that could also regularly bring us into closer contact with regions of higher density. The most famous of these extinctions, the Cretaceous Paleogene event that wiped out the non-avian dinosaurs, was almost certainly caused by an asteroid or comet impact, proving that such external triggers are a real and potent force in Earth's history. The question is whether that impact was an isolated random event or the most recent strike in a recurring galaxy-induced bombardment. However, this captivating narrative of celestial clockwork is far from settled science. Critics of the hypothesis point to significant challenges. For one, accurately dating ancient extinction events with the precision needed to confirm a strict 26 million year cycle is incredibly difficult. The further back in time we look, the more the geological record becomes fragmented and uncertain, making it hard to distinguish a true periodic signal from a random clustering of events. Furthermore, the timing of our solar system's passage through the spiral arms is also a subject of debate. The structure and rotation of the Milky Way's arms are complex and not perfectly understood, and pinning down exactly when Earth was in an arm versus an inter-arm region hundreds of millions of years ago is a formidable task. Some models suggest the correlation between spiral arm crossings and known extinction events is weak or inconsistent. The galaxy is a dynamic and crowded place, and our solar system's journey through it is fraught with other potential hazards beyond just spiral arms. Another compelling theory suggests that the primary trigger for comet showers might not be the spiral arms at all, but rather the gravitational influence of a hypothesized stellar companion to our Sun, a small, dim star nicknamed Nemesis. The idea is that this star, on a long, elliptical orbit, would periodically swing close to the Oort cloud, shaking loose a storm of comets before receding back into the darkness. While an intriguing concept, decades of searching have failed to turn up any evidence for such a companion, and the gravitational stability of its proposed orbit is questionable, leaving most astronomers skeptical. Other cosmic dangers, like passing too close to a wandering giant molecular cloud or even a nearby supernova, could also disrupt the Oort cloud, but these are inherently random events, not the kind of precise clockwork suggested by the extinction periodicity data. Ultimately, the theory of the galactic year influencing life on Earth sits at a fascinating intersection of astronomy, geology, and biology. It represents a shift in perspective, forcing us to consider that the fate of our planet may be intertwined with the grandest scales of the cosmos. While the evidence remains circumstantial and the debate is ongoing, the very possibility adds a profound new layer to our understanding of Earth's history. It suggests that the rise and fall of dominant species, the very narrative of life itself, might not be a story contained solely on our world. It could be a tale written in the slow dance of stars and the gravitational tides of the galaxy, a reminder that we are not just inhabitants of a planet, but passengers on a spaceship orbiting a galactic center, subject to the rhythms and cycles of a universe far larger and more connected than we often imagine. But our planet is constantly being bombarded by more than just wandering comets. It is under a relentless, invisible rain of atomic shrapnel from the most powerful explosions in the universe. This brings us to our 21st mystery, the baffling nature of ultra-high-energy cosmic rays. Imagine a single subatomic particle, a proton or the nucleus of an atom, carrying so much kinetic energy that it rivals a well-thrown baseball. This is not an exaggeration. The most energetic cosmic rays ever detected possess the energy of a fastball, but compressed into a particle a trillion times smaller than a grain of sand. These are the universe's ultimate bullets, and their existence pushes the very limits of what we believe is physically possible for a single particle to achieve. The energies involved are mind-boggling, reaching levels millions of times greater than what the most powerful human-built particle accelerator, the Large Hadron Collider, can produce. Every second, thousands of these particles pierce our atmosphere, but the ones at the very peak of the energy spectrum are extraordinarily rare. You might have just one particle of this caliber falling on a square kilometer of Earth each century. The central puzzle is a simple one. What cosmic cannon could possibly fire a particle with such unimaginable force? The mechanisms that could accelerate a single proton or atomic nucleus to such a velocity must be almost unbelievably powerful. Theorists point to the most cataclysmic events known to science. One prime candidate is the active galactic nucleus, the supermassive black hole at the heart of a distant galaxy, as it voraciously consumes surrounding matter. The intense magnetic fields and relativistic jets associated with these monsters could, in theory, act as a natural particle accelerator of cosmic proportions, speeding up charged particles across vast distances. Another potential source is the gamma-ray burst, the most luminous electromagnetic event since the Big Bang, which signifies the birth of a black hole in a hypernova, or the merger of two neutron stars. The shockwaves from such an explosion could potentially impart these tremendous energies to surrounding particles. Yet, despite these compelling theoretical sources, pinning down the actual origin of any specific ultra-high-energy cosmic ray has proven to be one of the most frustrating challenges in modern astrophysics. The primary reason for this difficulty lies in the nature of the particles themselves. Cosmic rays are overwhelmingly charged particles, primarily protons and atomic nuclei. And charged particles have a critical vulnerability on their long journey through the cosmos. They are deflected by magnetic fields. The Milky Way is permeated by a complex, tangled web of magnetic fields, as we've discussed. As a high-energy proton travels across millions of light years, it doesn't follow a straight path from its source to our detectors. Instead, its trajectory is bent and scrambled, twisted into a random walk by these invisible magnetic forces. It's as if you were trying to trace a single drop of water back to its origin in a storm cloud, but the wind had blown it in 1,000 different directions along the way. By the time an ultra-high-energy cosmic ray finally strikes the top of Earth's atmosphere, all information about its original direction has been completely erased. We know it came from somewhere out there, but its path is a scrambled mess, pointing back not to a single source, but to a blur of possibilities across the sky. So, how do we even begin to hunt for these cosmic snipers? Since we cannot observe the primary particle directly from space, we rely on its dramatic death. When an ultra-high-energy cosmic ray collides with a nucleus in the upper atmosphere, it triggers a spectacular cascade of secondary particles. This creates an avalanche of electrons, photons, and muons that spreads out over several square kilometers by the time it reaches the ground, a phenomenon known as an extensive air shower. To catch these fleeting events, scientists have built some of the most ambitious and sprawling observatories on Earth. The Pierre Auger Observatory in Argentina, for instance, covers an area of 3,000 square kilometers, a region larger than some small countries, with an array of 1,600 water tanks that detect the faint glow of Cherenkov radiation from these passing particle showers. Meanwhile, telescopes overlook the array to capture the faint ultraviolet fluorescence light that the shower produces as it develops in the air. By combining the data from the ground array and the fluorescence telescopes, scientists can reconstruct the energy, direction, and nature of the primary cosmic ray with remarkable precision. But even with these colossal detectors, the mystery has only deepened. One of the most significant findings from the Pierre Auger collaboration was a weak correlation between the arrival directions of the highest energy cosmic rays and the locations of nearby active galactic nuclei. This was a tantalizing hint, suggesting that these monstrous engines might indeed be the long-sought accelerators. However, the correlation is not perfect, and many events do not point back to any known celestial object, leaving room for other exotic explanations. Some theories have even proposed that these particles could be the signature of the decay of super-heavy, hypothetical relics from the Big Bang, or the product of cosmic strings, topological defects in the fabric of spacetime itself. The hunt is further complicated by the Greisen-Zatsepin-Kuzmin, or GZK, cutoff. This is a theoretical limit that suggests that the highest energy protons should not be able to travel more than about 150 million light-years through the cosmos. They would lose energy by interacting with the photons of the cosmic microwave background, the leftover radiation from the Big Bang. This means that the very highest energy cosmic rays we detect must come from relatively nearby sources within our local supercluster of galaxies. This shrinks the cosmic haystack we have to search, but finding the needle within it remains as difficult as ever. The enigma of ultra-high-energy cosmic rays is a humbling reminder that the universe is capable of generating forces of acceleration that we can barely comprehend, and that the answers to some of our biggest questions are raining down upon us all the time, encrypted in particles smaller than an atom. Yet even as we consider the voids that our galaxy may drift through, we must look beyond our own island universe to confront one of the largest and most startling structures in the entire observable cosmos, a place of such profound emptiness it has earned the dramatic nickname, the Great Nothing. This is the Boötes Void, and while it lies far beyond the boundaries of the Milky Way, its staggering scale and implications are deeply connected to our understanding of the cosmic web that our galaxy is woven into. Picture a sphere of space so vast that it would take a beam of light 330 million years to travel from one side to the other. Within this unimaginable volume, you would expect to find thousands of galaxies, perhaps even tens of thousands, based on the average density of the universe. Instead, the Boötes Void contains only a few dozen. It is a cosmic desert of staggering proportions, a bubble of near nothingness that challenges our very conception of what the universe should look like. The discovery of this void in the 1980s was a complete shock to astronomers. When mapping the large-scale distribution of galaxies, they found this gaping hole in the constellation of Boötes, a region of the sky that was inexplicably dark. Later, more sensitive surveys confirmed the void's reality, cataloging only around 60 galaxies within its bounds, where standard cosmological models predicted there should be closer to 2,000. This isn't just a slightly underdense region. It is a colossal anomaly. To grasp its scale, if our Milky Way were located at the center of the Boötes void, our own discovery of other galaxies would have been a much more recent event in human history. The nearest major galaxy, Andromeda, would be just beyond its edge, and without the myriad of other nearby galaxies to study, our entire understanding of the cosmos would have developed much more slowly. The void's existence immediately raised a fundamental question. How does something this big and this empty actually form? Scientists have proposed two primary theories to explain this great emptiness, both rooted in the dynamics of the early universe. The first theory points back to the initial moments of cosmic inflation, that period of exponential expansion, a fraction of a second after the Big Bang. During this phase, quantum fluctuations were stretched to enormous sizes, seeding the regions that would later collapse into galaxies and galaxy clusters. It is possible that the Boötes void represents an exceptionally large, primordial underdensity, a region where, by sheer random chance, the initial quantum fluctuation was a trough rather than a peak. In this scenario, the void has been largely empty since the very beginning, its vast volume simply lacking the initial density required to form a significant number of galaxies. The second, and perhaps more compelling, theory suggests the void is not a single, pristine emptiness, but the result of a cosmic merger. Imagine smaller voids, like soap bubbles, coalescing over billions of years. As the universe evolves, gravity pulls matter into filaments and clusters, leaving behind expanding voids. These voids can grow and run into each other, their boundaries merging to form ever larger empty regions. The Boötes void could be the end product of several smaller voids merging together, their combined volume creating the colossal spherical emptiness we observe today. This void merger scenario is supported by the observed distribution of the few galaxies within the void. They aren't completely random, but appear to form a faint, tubular structure that some astronomers have likened to a river of galaxies flowing through the desert. This could be the remnant of the filamentary wall where smaller voids once met and merged. The existence of the Boötes void, and others like it, forces a critical reevaluation of the cosmological principle, the foundational idea that the universe is homogeneous and isotropic on the largest scales. A void of this size certainly tests the meaning of large scales. If such immense emptiness is a common feature of the cosmos, it suggests that the universe has a frothy, bubbly structure with variations in density far more extreme than we once thought. The Milky Way, in this context, does not reside in an average neighborhood. We are situated within a galactic filament, part of the Laniakea supercluster, which is itself one of the dense walls surrounding the KBC void we discussed earlier. Our perspective is inherently biased. We live in the cosmic equivalent of a bustling city, and it is from this vantage point that we are trying to understand the vast, empty countryside between the metropolitan centers. The Boötes void is a stark reminder that the universe is not a uniform soup, but a complex network of dense clusters, winding filaments, and vast, empty voids, a cosmic web in which our entire galaxy is but a single luminous thread. For all its current majesty and seeming permanence, the Milky Way is not an eternal monument in the cosmos. It has a date with destiny, a future written in the inexorable pull of gravity that will ultimately erase its iconic spiral form forever. In about 4.5 billion years, our galaxy is set to collide with its largest neighbor, the Andromeda Galaxy, an event that will trigger the most spectacular celestial transformation our corner of the universe has ever witnessed. This isn't a speculative possibility. It's a firm prediction based on decades of painstaking observations from the Hubble Space Telescope. which has precisely tracked the motion of Andromeda and confirmed it is on a direct course for us. Think of two immense star cities, each containing hundreds of billions of suns, slowly but surely drifting toward a cosmic union that will completely reshape the local galactic landscape. The prospect of two galaxies colliding might sound terrifying, a celestial catastrophe of unimaginable proportions. Yet, the reality for any planetary systems within them is almost certainly not one of fire and brimstone, but of breathtaking celestial spectacle. This is because galaxies are overwhelmingly empty space. The average distance between stars is so vast that a direct stellar collision during the entire multi-billion-year merger process is incredibly unlikely. If you were standing on a planet like Earth 4 billion years from now, the night sky would transform gradually over millions of years. The Andromeda Galaxy, which today appears as a faint, fuzzy smudge in the constellation that bears its name, would grow larger and brighter with each passing epoch, eventually filling half the sky as a shimmering, sprawling disk of countless stars. As the galaxies first swing past each other in a gravitational dance, their spiral arms would be grotesquely distorted by tidal forces, stretched into long, streaming tails of stars, flung out into the intergalactic void. The sky would be a chaotic canvas of new star clusters and glowing pink nebulae as the collision compresses vast clouds of gas, triggering a fireworks display of stellar birth on an unprecedented scale. This violent, beautiful dance will not be a single, clean impact, but a series of close passes over hundreds of millions of years. With each gravitational encounter, the galaxies will lose orbital energy, gradually spiraling inward until they finally merge into a single, new structure. The elegant spiral disks of both the Milky Way and Andromeda, dependent on a delicate, rotating equilibrium, will be utterly destroyed in this process. The resulting galaxy will be a massive, amorphous ellipsoid of stars, a classic elliptical galaxy. Astronomers have already given this future hybrid a nickname, Milkdromeda, or sometimes Milkomeda. This new galaxy will be a testament to the violence of its creation, a vast collection of stars orbiting in random, plunging paths rather than the orderly, circular motions within a disk. The era of grand spiral design in our local group will be over, replaced by a more common, though still magnificent, elliptical giant. What does this ultimate fate tell us? It is the final, definitive proof that galaxies are not static islands, but dynamic and evolving systems. The serene spiral we see today is merely a phase in a long life cycle dominated by interaction and merger. Our own Milky Way's past is littered with evidence of such cannibalism, from the Gaia sausage to the ongoing consumption of the Sagittarius dwarf. The collision with Andromeda is simply the next and largest chapter in this ongoing story of hierarchical growth. Large galaxies are built by absorbing smaller ones, and occasionally, two giants will combine to create something entirely new. This destiny also provides a profound perspective on our place in the cosmos. The entire timeline of life on Earth, from the first single-celled organisms to the rise of human civilization, has unfolded in a relatively quiet and stable period of our galaxy's history. We exist in a cosmic golden hour, a peaceful chapter between the violent construction of the past and the colossal merger of the future. By understanding the fate of the Milky Way, we come to see our galactic home not as a permanent fixture, but as a fleeting, beautiful structure in a universe of constant, majestic change. Continuing our journey through the Milky Way's greatest mysteries, we come to a star that, for a brief and electrifying period, seemed to offer the most compelling evidence yet for an advanced civilization beyond Earth. This is the story of KC 8462852, more famously known as Tabby's star, or the alien megastructure star. Located about 1,470 light-years away in the constellation Cygnus, this seemingly ordinary star became an interstellar sensation in 2015 when data from NASA's Kepler Space Telescope revealed it was doing something that no other star in the galaxy was seen to do. Kepler's primary mission was to find planets by detecting the subtle periodic dimming that occurs when a planet passes in front of its host star. But Tabby's star didn't dim in a neat, predictable way. It exhibited wild, chaotic, and drastic dips in its brightness. Some of these dips were astonishingly deep, blocking up to 22% of the star's light. To put that in perspective, even a Jupiter-sized planet would only block about 1% of a sun-like star's light. What could possibly be large enough and irregular enough to cause such a signal? The most tantalizing and admittedly sensational hypothesis was that we were seeing evidence of an alien megastructure, a vast, orbiting swarm of solar collectors known as a Dyson sphere, under construction by a Type II civilization on the Kardashev scale. This extraordinary idea didn't emerge from a vacuum. It was a direct response to the extraordinary data. The light curves from Kepler showed a series of small, sharp dips, and then, most famously, two colossal dimming events, one that dropped the star's brightness by 15% and another, later on, by a staggering 22%. These events were asymmetric, meaning the star dimmed more gradually than it brightened, and they were completely aperiodic, with no repeating pattern. Natural explanations had a very high bar to clear. A young star might be surrounded by a clumpy, irregular disk of dust and debris, but Tabby's star was not young. Its spectrum showed it to be a mature main sequence star, and it lacked the excess infrared radiation that such a dusty disk would produce. A family of giant comets was another leading natural theory, suggesting that a swarm of them, with vast, dusty tails, could be passing in front of the star. While plausible, the scale required was immense, needing the equivalent of hundreds of giant comets to account for the deepest dips, a scenario that struck many as statistically very unlikely. With the most conventional explanations struggling, the door was opened, however cautiously, to more speculative possibilities. The scientific team, led by astronomer Tabetha Boyajian, after whom the star is nicknamed, famously stated in their paper that alien megastructures were a plausible scenario worth considering. The story exploded across the globe, capturing the public's imagination like no other astronomical discovery in recent memory. What happened next was a beautiful demonstration of how modern science operates in the 21st century. Rather than dismissing the alien hypothesis out of hand, the scientific community did exactly what it should do. It went looking for more data. A massive, multi-wavelength observational campaign was launched, involving both professional observatories and a grassroots army of citizen scientists. Dr. Boyajian herself turned to the public, launching a highly successful Kickstarter campaign that raised over $100,000 to secure dedicated time on a global network of ground-based telescopes. This allowed for continuous monitoring of the star, catching it in the act of dimming again and again. Amateur astronomers around the world pointed their own telescopes at Tabby's star, contributing invaluable data points and alerting the professionals when a new dip was beginning. This collaborative effort was crucial, creating a rich, long-term dataset that held the key to solving the mystery. The critical clue came from analyzing how the star dimmed across different colors, or wavelengths of light. If a solid, opaque object like a planet, an asteroid, or even a solid megastructure were passing in front of the star, it would block all wavelengths of light equally. However, the observations told a different story. When the star dimmed, it dimmed more significantly in blue light than in red light. This is a classic signature of dust. Tiny dust grains are very effective at scattering shorter, bluer wavelengths of light, much like our own atmosphere scatters blue light to make the sky appear blue, while allowing longer, redder wavelengths to pass through more easily. This finding was a major blow to the alien megastructure hypothesis, which predicted a mostly wavelength-neutral dimming. The data strongly pointed toward a natural culprit, a vast, irregular cloud of fine dust particles orbiting the star in a complex and clumpy configuration. Subsequent observations, particularly with the Las Cumbres Observatory Global Telescope Network, solidified this dusty picture. They revealed that the star experiences dips on many different timescales and depths, all showing this same telltale reddening effect. The current leading model suggests that Tabby's star is surrounded by a giant, broken-up ring of dust, perhaps the remnants of a shattered moon or a catastrophic planetary collision. The deep, historic dips observed by Kepler could have been caused by a particularly dense clump of debris from such an event, while the ongoing, smaller dips are from more diffuse clouds. There is also evidence that the long-term, secular dimming of the star, a slight but steady fading over the century, could be explained by a giant, dusty cloud on a wide, eccentric orbit, perhaps taking hundreds of years to complete a single pass in front of the star from our vantage point. While the exact origin of all this dust remains an active area of research, the consensus has firmly shifted away from aliens and toward a complex, dusty astrophysical phenomenon. The legacy of Tabby's star, therefore, is far greater than just solving one mystery. It stands as a powerful case study in the scientific method. A strange signal was detected. All plausible explanations were considered, and then the community rallied to collect more data, allowing the evidence to guide the way to a natural conclusion. It demonstrated the vital role of public engagement and citizen science in advancing our understanding of the cosmos. And perhaps most importantly, it showed that the universe is still capable of producing phenomena so strange that they push us to the very edge of our imagination, forcing us to question, to explore, and to collaboratively seek the truth, no matter how fantastic the initial possibilities may seem. And as we bring our galactic journey toward its close, we encounter what is perhaps the most philosophically profound mystery of all, a cosmic alignment so peculiar and so unsettling that it has been given a name straight out of a thriller, the axis of evil. This phenomenon doesn't involve a black hole or a wandering star, but something far more fundamental, the very afterglow of creation itself, the cosmic microwave background. This faint, cold radiation is the oldest light in the universe, a snapshot from just 380,000 years after the Big Bang, and it has been the cornerstone of modern cosmology, confirming our models of the universe's origin and expansion. Yet, when scientists built exquisitely sensitive instruments to map its minute temperature fluctuations, the tiny seeds that would grow into all the galaxies and clusters we see today, they found a pattern that has stubbornly refused to fit the standard narrative. The core assumption that is being challenged is the cosmological principle, the idea that the universe, on the largest scales, is isotropic and homogeneous. This means it should have no preferred direction, no special axis, no up or down. It should look the same in every direction, a perfectly random and fair cosmic lottery. The pattern of hot and cold spots in the cosmic microwave background should therefore be just that, random. But when researchers began analyzing the data from satellites like NAS, a Wilkinson microwave anisotropy probe, and the European Space Agency's Planck mission, they noticed something bizarre. The fluctuations weren't completely random. They appeared to be subtly aligned, or correlated, along a particular axis that slices through the cosmos. This in itself would be strange, but the truly unnerving part is where this axis points. It appears to be aligned with a statistical significance that is hard to dismiss as mere chance, with the plane of our own solar system and the direction of the sun's motion through the galaxy. It's as if the universe's oldest fossil, has a mysterious arrow painted on it, and that arrow is pointing directly at us. This apparent alignment is deeply troubling because it seems to suggest that our position in the cosmos is, in some fundamental way, special. It resurrects the ghost of a pre-Copernican universe, where Earth was the center of everything. Modern science has systematically dismantled that idea, showing we orbit an average star in an average galaxy, in a universe with no center. The axis of evil, if it is real and not an illusion, throws a wrench into this entire worldview. Why would the grandest possible structure of the universe, the imprint of its very first moments, care about the trivial orientation of our little solar system? The implication is that either we are, against all odds, in a privileged position, or there is something fundamentally wrong with our understanding of the cosmos's first moments. This isn't just a minor anomaly, it's a potential crack in the foundation of cosmology itself. So, what could possibly explain such a strange correlation? The scientific community has approached this puzzle with a healthy dose of skepticism, exploring every possible avenue, from the mundane to the revolutionary. The most conservative, and therefore most favored, explanation is that it's a colossal statistical fluke combined with some form of observational bias. The cosmic microwave background maps are incredibly complex, and when you process the raw data, you have to subtract foreground signals light from our own Milky Way galaxy, for instance. It's possible that our models for this foreground subtraction are imperfect, leaving behind a residual signal that mimics a preferred axis. Alternatively, it could be that the way we process the data to remove the dipole, the signal caused by our own motion relative to the cosmic microwave background, is inadvertently introducing this strange alignment. Proponents of this view argue that the universe is vast, and sometimes, just by pure chance, random patterns can appear to have a structure. They point out that the statistical significance, while notable, isn't overwhelmingly high, and that future, more precise data could make the anomaly disappear. However, if the alignment persists and is confirmed to be real, the explanations become far more dramatic and would require a fundamental rewriting of our cosmic history. One radical possibility is that the universe is not isotropic on the largest scales. It could be that the fabric of spacetime itself has a preferred direction, perhaps due to the influence of a vast, unseen structure from before the Big Bang. This could mean our observable universe is just a small patch of a much larger, anisotropic cosmos, and the axis of evil is a glimpse of that grander, lopsided structure. Another mind-bending theory involves cosmic topology, the idea that the universe might be finite and have a complex shape, like a hall of mirrors. If the universe is much smaller than we think but wrapped around itself in a certain way, light could travel along multiple paths, creating patterns and correlations in the cosmic microwave background that would appear as a preferred direction from our limited vantage point. This would mean the entire cosmos is a finite, if unimaginably large, structure with a discernible geometry, and the axis of evil is a clue to its true shape. The debate over the axis of evil remains one of the most contentious in modern cosmology precisely because the stakes are so high. It pits the clean, elegant simplicity of the standard model against a messy, complicated, and potentially revolutionary alternative. To resolve it, we need more than just better maps of the cosmic microwave background. We may need entirely new kinds of observations, perhaps of the gravitational wave background from the Big Bang, or of the large-scale distribution of galaxies and quasars at even greater distances. For now, the axis of evil stands as a profound and humbling reminder. It tells us that even our most successful and well-tested theories of the cosmos might be incomplete. It is a lingering question mark written across the entire sky, a whisper from the dawn of time suggesting that the universe might still hold secrets about its fundamental nature that we are only just beginning to perceive. And so our incredible journey across the galaxy comes to a close. For now, we have ventured from the immense gravitational pull of the Great Attractor to the violent heart of our own galactic center, from the ghostly whispers of dark matter to the brilliant, fleeting flashes of magnetars. We have encountered phantom planets, debated the nature of interstellar visitors, and even questioned whether the very blueprint of the universe hints at our own significance. What this tour reveals is not a collection of isolated curiosities, but a single unifying truth. The Milky Way is a living, breathing, and profoundly dynamic entity, filled with processes and puzzles that are actively shaping our cosmic home. Each mystery we have explored is far more than a simple question mark. It represents a fundamental frontier of human knowledge. The hunt for Planet 9 is not just about finding another world. It is an archaeological dig into the violent early history of our solar system. The struggle to understand dark matter is not merely an academic exercise. It is a quest to identify 95% of the universe's content, the very fabric of reality that we have so far failed to grasp. These are not dead ends, but open doors, invitations to push the boundaries of physics and redefine our place in the cosmos. Every time we solve one cosmic riddle, the universe presents us with 10 more, each more baffling and beautiful than the last. The resolution of the Pioneer anomaly through painstaking engineering analysis showed us that the answers can be subtle, hidden in the intricate details of our own creations. The ongoing saga of Tabby's star demonstrated how a single, strange signal can mobilize a global community, blending professional science with public passion to chase down the truth, even when that truth turns out to be dust instead of aliens. This relentless cycle of question and answer is the very engine of scientific progress. It is a testament to our innate human drive to explore, to understand, and to never be satisfied with the limits of our current knowledge. The Milky Way, in all its majestic complexity, is the ultimate classroom and the ultimate laboratory, offering endless lessons in humility, wonder, and the sheer joy of discovery. This brings us to the most important part of our journey: what you do next. The next time you find yourself under a clear, dark sky, look up at that shimmering band of the Milky Way arching overhead. Remember that you are not just looking at a static picture. You are gazing into a vast, dynamic ecosystem of runaway stars, cannibalized galaxies, invisible matter, and stellar nurseries. You are seeing the same cosmic river that has inspired humanity for millennia, but you now see it with new eyes, aware of the incredible secrets it holds. Let that sight fill you with a renewed sense of wonder and an insatiable curiosity. The greatest tool we have in this grand exploration is not a telescope or a supercomputer, though those are vital. It is a curious mind. Stay hungry for knowledge, question what you know, read about new discoveries, and allow yourself to be amazed by the sheer strangeness of the universe we call home. The adventure does not end here. Our channel is dedicated to continuing this voyage to the edges of understanding, diving deep into the universe's greatest enigmas, from the quantum strangeness of black holes to the large-scale structure of the cosmos itself. If this journey through the Milky Way's mysteries has sparked your imagination, then be sure to join our community of explorers. Subscribe to the channel and hit the notification bell so you don't miss our next deep dive into the unknown. The cosmos is vast, the questions are endless, and together we can continue to unravel its most extraordinary secrets. Thank you for watching.